today's speaker, Alex Mathis, is the partner of the talk we heard yesterday, so they're bookends. But you'll see that they have a lot in common. They help each other, and in more than one way. It's a beautiful couple, and they both won the Kendall Prize, which was given out earlier this year. And Eric Kendall was there. So who here doesn't know who Eric Kendall is? Okay, well, you're missing something. No, he's a force of nature. Not only did he win the Nobel Prize, physiology and medicine, but he also has written books, and not just about science, but also about art.
Yes.
Yeah. And he's also an extraordinarily good speaker and a representative to the public, because he's so charismatic, and he has an even stranger laugh than I have. So he's been an old friend for a long time, but I should be introducing you, but this is a great honor, and we're really pleased to have Alex here.
It is really an honor for me to be here. I really greatly enjoyed all the talks this week, and I think they will tie with several of the points that I'm going to make in this talk. And I hope we will have really exciting discussions. So what I'm interested in Mackenzie, and I think many other people, is understanding sensory motor control. And I'm going to make a point that, machine learning is obviously helpful for this. Wow, not surprising, I guess. Biomechanics simulators, I think, are really, really helpful for this. And they actually got much better and much faster. And I will show you stuff along those lines. So what is the problem I'm trying to solve? In my lab, we're interested in picking low-hanging fruit. But we're interested not in controlling point masses and doing this, but we're interested in kind of taking into account as much as possible the real biomechanics. Because, well, on the one hand, because it's extremely challenging, and on the other hand, because I believe, and I think others believe that too, that, here's the fact, body and brain co-evolved. So most likely they shaped each other. And so if we do take into account biomechanics at skeleton when we study motor control, we might actually learn something about neural circuits that we could otherwise not learn. That's the basic thing. Just to give you an idea why this is extremely hard. For example, for the human body, there are 600 muscles. So in other words, our brains control 600 degrees of freedom. You can it's actually sometimes even more, because per muscle is in kind of pools and so on. The musculoskeletal system is, of course, highly redundant. There are many muscles that act on the same joints. There are some muscles that act across multiple joints. One of my favorite muscles is actually here, and it can pull the fingers. And it's the same muscle that has then a tendon that splits out, that goes along here and goes along all the fingers out and connects to the tip. One muscle. Is that to the tip on the fingers? Yes. And it's the tip. Well, it's to the tip, and then there are actually muscles here, and it connects to those muscles. I'm sorry. Oh, it's inside the finger also, or not? Yeah. There are muscles in the finger. And so this is, for example, a multi-articular muscle. Really interesting muscle. Another thing that makes it challenging is, of course, that sensing of the body state. So it's not just the control is very distributed, but also sensing is highly distributed, of course. And I'll talk a lot about that. And of course, the time delays for perception and actions, and we've beautifully talked about this week. I'm not going to have any time delays in this work, but of course, they play a fundamental role. So it's clear. So how does the brain do that? In the end of the day, the brain takes into account anything it can, any form of sensory feedback that it has, and it probably exploits it to do motor control. And specifically, because I don't want this talk to be a surprise, I want to tackle two questions. I will tell you those two questions right away. And the first one is just related to proprioception, but of course, proprioception is fundamental for doing motor control. And the question is, what computational goal best explains proprioception? That's the question, the first question I want to tackle. And let's see if it makes sense and should like the answer. And the second question is, how can we come up, and this is actually more machine learning part, how can we come up with better control policies to control extremely high dimensional X-rays? Now, if you want to control 600 degrees of freedom, yeah, there's some open problems, of course. So let me start. So the first part is about perception, okay? Or it's about sensing, namely about proprioception. And let me start with vision. And let me start with a beautiful article by Terry and Patricia Churchland and Ramanathan. And it's called A Critique of Pure Vision. Okay? And as you know, there are some scientists out there that believe that the goal of vision of any sensory system, in some sense, is to create a detailed model of the world. Okay? And they have a beautiful sentence in this article. And they say, the idea of pure vision is a fiction. We suggest that it obscures some of the most important computational strategies used in the brain. Yes. So, what is the alternative to pure vision in this sense that a sense actually creates a detailed model of the world? The alternative view, one alternative view is kind of a utilitarian or also information theoretic point of view, where you would argue, well, okay, you have a sense or you have a sensory stream. And the point of that sensory stream is actually to provide useful information for whatever you want to do in later parts of your brain in order to act on it. That's why I kind of call this utilitarian approach. And, or you could, of course, also do it information theoretically. And so,
Yeah, that's not information theoretic.
yes, next slide.
The genius of Shannon was he said, let's forget what's useful. But anyway, go ahead.
Right.
We'll talk about that later.
No, no.
So I love what you're saying. So
No. This next slide is actually exactly going to pronounce it for you. Wondering. So how can we, some normative models where we say, well, okay, let's say we study vision and we want to build a system that is optimized according to a certain objective, be it information theoretic or utilitarian. We can build a candidate system and then we can study the candidate system and see if it's better aligned or worse aligned with knowledge. That's an approach. That's a very fundamental approach that goes back to, that's some lag here. To Barlow and many others. So right out of the gate when information theory emerged, neuroscientists have made really interesting arguments on this. And so in the sense of information theoretic arguments, one very famous argument is, of course, the efficient coding argument, which goes back to Barlow indeed, and who argued that, well, sensory systems should be optimized for the statistics of the world. Okay? And one very famous example, but there are many, many beautiful studies in this direction, is actually a paper by Olshausen and Field in Nature in 1996. And what they showed is that, well, if you build a very simple visual system, it's actually a hidden single layer autoencoder, it's actually linear. And you build it such that you sparsely encode naturalistic image patches, then you get these kind of filters. And you all have been in the vision talk yesterday. These are simple cells. So if you start with the normative goal of saying, well, all maybe the vision is doing is sparsely representing the world, you've explained something about the features in early visual areas. And there have been thousands of studies, I'm sure, of this. There's some nice reviews here mentioned. For example, if you do, Terry has a nice paper when if you use ICA, you also get simple cells if you do ICA so on image patches. One challenge for this information theoretic approach was actually to scale it. I mean, this you agree, John, that this is an information theoretic.
Oh, yeah, absolutely.
Oh, good. The challenge was, well, okay, we do know that vision is not a single layer. It has few layers and many stages. And so people have tried for a long time to kind of train multiple layers with information theoretic goals and then see if they can align it to what happens in vision. And that was not the most successful thing.
So I think it's also worth pointing out that even in, V1 or layer 2, 3 of V1, there's so many neurons, you have massive redundancy. And so that sensory code is actually not efficient in the sense.
That's what we.
Okay, so, well, there's two problems, okay, that you should separate, which is that you have this, optic nerve, then it has a very limited bandwidth, right? It's about 1 million microns in it, but the fact is that's where information theory comes in. How to go from transmit information over a narrow bandwidth. But once you get to the cortex, now that's not the goal anymore. The goal is to re-represent things in an efficient way. And that's why redundancy, represent it in multiple different ways. And also, all right, because of the fact that there's recurrent interactions, right? That's not information theory anymore.
That's
right. Whereas this receiver transmitter, but it's really computation.
right. And I should also say, especially efficient coding was extremely successful for explaining the retina. Therefore, because of this clear constraint with the optic nerve, but also in many other sense, actually, we gain many insights.
And also, other concepts like the economics principle, biomechanics work, where you really reduce mutual, like maximize mutual, then minimize mutual information with that trade-off. Is that relevant?
Okay, totally relevant. I think we could give many talks just on that topic, and much work has been done. So an alternative approach that is not information theoretic is what people call task-driven modeling. Okay? That's more utilitarian. The idea is, well, let's assume you have some hierarchical neural network, and let's assume that hierarchical neural network has particular goals. A goal. Let's say it's in a mouse, and the mouse really wants to detect cats to run a window. Okay? I'm giving you a real example in a second. Then you can take that objective, train up your system, and then compare that system to the visual system of us. And here I want to highlight an interesting kind of analogy between machine learning and brain models in some sense, which is, I think everyone here knows, a machine learning model consists of 4 parts. Its architecture, its task objective, the data set you train it on, and then the optimization method. Okay. And you can make an analogy that perhaps the brain or circuit is, a particular part of the brain is a particular circuit that needs to do something in its ecological niche. Okay? And the data set is the environment that its species is embedded in, and this is ecological niche. And that circuit might be optimized through natural selection and synaptic plasticity and many, many other things. And you can see that these 4 parts, you can pick and choose and create all kinds of models, give you brain models. And one of the, and so there's this analogy, and in task-driven modeling, I think the biggest success was something that was beautifully criticized yesterday. But let me show you some of the success. Again, it's this work from Jim DiCarlo's lab and Dan Yeamans that started in 2014, essentially. But here I'm highlighting a later paper from these 2 authors, where they actually used many more methods and compared to many more areas of the ventral pathway. So what we have here is the ventral stream of a macaque. They study a very specific, or they want to explain the neural code in a very specific task of vision, which is core object recognition, as they call it. That is, the monkey is the monkey does not saccade, so it's actually not natural vision in that sense. Okay, so you will present the monkey with a picture like this, where there's an object in the center, there will be clutter around, and the monkey, and you can also control, of course, how long you show the scene. So you can actually, in that sense, because you can keep that window relatively short, you mostly engage feed-forward circuits into the visual pathway just through an argument of timing. So that's what they want to. So they study both the behavior of core object recognition, that say, how well can monkeys do that task? And also they want to then explain the neural code along this pathway. And I think a very simplified picture would be that before the Yeamans work, we had good models of V1, V2, and V4. I mean, of course,
many open questions, but reasonable models. And we didn't really have good models of IT. People considered IT neurons to be really complex, and it's not really clear how you can actually explain their tuning properties. And so the basic idea of them was, well, what if we take neural network models, here let's say a CLAN, and we train them on object recognition. And this doesn't have to, these images that you use for training is much, they don't have to be pictures that you then actually show to the monkey, okay? So you pre-train the model on a particular task, let's say image recognition, then you freeze the weights. And now what you do is, because you actually had this psychophysical task with your monkey, you can show the same picture to your neural network. And then at various spots of your neural network, let's say here, I can extract the representation of a bunch of images. And what they did is they did linear probing in the sense that, in the following sense, that on some training stimuli, they extract these intermediate representations. They have neural recordings for different pictures in these different areas, and they linearly regress from this representation against these neurons and try to predict how many spikes does this neuron fire on that particular picture. And again, the training of your linear readout here is done on a set of pictures. That is the training set. And then what you really do is you test how well this linear probing works on images you have not shown to your model and to your linear readout. Okay? And the core insight from their work was that this works really well. Namely, you can explain V1, you can explain the neural code of V1 with very high accuracy, V4 and IT. And actually black here is exactly what I talked about. It's models that are trained on object recognition in a supervised fashion. And so here they have images and labels.
It's a model fit forward.
It's purely feed forward. So this is actually specifically in this paper, this is a resonant 8E. Okay. And as a matter of fact, if you don't train the resonant 18, then this is this gray bar, that is brown bar. So if you just randomly initialize your rates resonant 18, you're not so bad actually at explaining visual responses. No, I mean 0.7 explained variance, it's not that bad. Interestingly, if you train it supervised, you don't also get that much better. Well, the deeper you go, the more gain you have. And then one interesting point,
You're doing a lot better in IT than you want. I mean, I don't understand something here. They're going to tell me.
why? Why is that surprised? I mean, it makes sense because the untrained,
Probably like stupid.
no. I mean, the untrained model cannot do object recognition. It's just that CNN with random filters. So
So one of the problems with this is you damage IT, take it out, and ask them to do simple categorization, which is what we've done. They can do it pretty well. They don't lose it. I thought they were going to be devastated. They're not.
right.
They'll do the same manipulation to one of these neural network models. You destroy its ability to do the work. So the question I got is, how much can you rely on this as a insight and that how you it might be the brain is to me. And the reaction to damage is so different.
That's a good question, and I think what the field should do and is doing now is to then do lesions on these models, build better models, try to.
What's the reasons it's on the monkeys?
I totally agree, and I think we could again discuss this for a very long time. What I do think is two things I think are interesting here. On the one hand, it's a very simple way, algorithmically speaking, to build a candidate model. Sure. Like you say, oh, I take ImageNet, I take a resonant 18, I train it, and then I have a filter bank. Does it work? And it works reasonably well. And for example, it also has a topography. If you look at the layers, this is layers from your resonant 18. Then the early layers are better at explaining V1. The intermediate layers are better at explaining V4, and the higher order layers are better at explaining IT. Now you could have kind of all kind of criticisms that, well, it in some sense makes sense. We know that, for example, before CLNs, the best way to recognize a picture was to show it to a monkey, record in IT, and train a linear readout. So is it surprising that you can align a good ResNet that can do object categorization with something that is also very good at object categorization?
But see, it's one question. When you're doing this,
Linear probing?
linear probing to kind of predict the fire rate of neurons. Like how many significant weights are there to units in the network? Like, is it kind of significant weights, just like a couple units, or is it like this graded combination of hundreds?
Yeah, I think it's typically not very sparse
And large. Yeah.
which I guess aligns well with the talk from yesterday, because I mean, in some sense, according to yesterday's talk, cortex is mainly continuous. CNNs are discrete. So yes, you can build up what you want, but you need to linearly combine quite a few things. But that's speculation.
Just quick question. Gentlemen, it's impressive. Something that's 6% explained in marketized value.
Yeah.
Does it bother you that putting in garbage, putting in grain, it's 70%?
Right. I think the more interesting side is over here. I mean, and also, randomly initialized CNN is not garbage. If I take, because it's a CNN, if I take a fully connected neural network and randomly initialize it, you will explain nothing. Here, nothing. Like a CNN, even if you make the filter random, has a lot of structure. So because weight sharing, it is visual filters. At the end of the day, that decide around. Even if the kernels are random batches.
So actually, one of the criticisms back in the 70s, it was that the perceptron really was limited, to linear discriminations, because it was only one layer. But actually, if you look at Rosenblatt's book, he said if you do a lot better, if you have another layer, you can initialize with random weights and don't train it, and it greatly improves the performance. And it's basically what you're seeing here, right? For these, untrained, random features that you put in. I mean, it's random features are not useless,
right? And that's the kernel trick, And if your random features have even more structure that are tailored for the problem, which in a random CNN is kind of the case, then you don't do that poorly, actually. But notice in IT you do. I mean, here you get a gain of almost 2x, for example, 5 trading. Anyway, I think I should move on. Didn't want to dwell too much on this work. I think the core point, read this beautiful paper from Terry on a critique of pure vision. And one argument is, well, maybe what vision actually does is it optimizes particular goals of the organism, and we can test those by actually making candidate models and comparing against the neural code. I should emphasize one thing. These, as everyone here knows, I mean, these CNNs they're not good models for psychophysics in humans. No. They're really good models mostly for explaining the neural code. Okay. One thing, maybe I skipped this, but I wanted to highlight that recent paper from our lab where we actually focus on a very challenging perceptual task, which is you need to make a 3D reconstruction of a hand and an object from a single picture. And as you can see, there are lots of occlusions, and we can do this pretty well and better than previous state of the art. This was actually just at CVPR a month ago or something. And so we state of the art on some benchmarks. But what is interesting, I think, about this paper and why I bring it up is that unlike prior work in this area, our intermediate representation is actually an implicit representation of the scene. It's not an explicit representation of the hand that you then refine. And so I do want to bring this up because in the context of, okay, what is the goal of vision? Okay, even if the goal is now to make a complete model of the world, it's not really clear how you do that in the brain. Like, what is that representation? It could be implicit, it could be explicit. There are many ways in which you can build it.
What does it mean?
Implicit and explicit.
Yeah.
Yeah. So here, this is an engineering paper, no? So here, explicit really is we actually have a CNN we have a neural network that in its weights parameterizes the surface field
In an abstract way.
in an abstract way. So it's a signed distance field. No, that's good. But that's all. Yes, there's no intermediate 3D representation here. It's just that it's really the weights itself represent the structure.
So you sort of model of what it is.
Yes, and then actually there's some. What's that?
A signed distance field is a classical representation of shape.
Yes, but it's not. I agree, but it's not an explicit one. We do, and I think in neuroscience people typically think, oh, there's really like a little homunculus there. Right. No, but it can look very different and still be the right representation. That's my point. I'm not questioning. Yes, this is the representation.
So, and this is actually a real problem conceptually, right? In other words,
Yes.
I mean, Meyer had this 2.5D sketch, right? The way Meyer was to try to solve it off was say, well, you're going to actually have a really explicit model of the surface, and that is going to be the representation. But when you go into the brain, you don't see that, right? What you see is a lot of features, and from that you can extract, because that's it has the information, right? But because you can't see it, right? It's very hard to even think about what's going on.
By the way, I once.
But how are you learning it here from touch or?
No. So this is a benchmark where you actually do have access to. Yes, that makes sense. It's part of the benchmark. People usually then use it at that stage to maybe use it here as an other output. But yeah.
But is it like your approach approach to others? But did you already say what's the essence of your approach? Or is it the country levels?
Well, this is, I would say, it's the first approach where in this specific benchmarks of 3D recognition where our representation is implicit here. And previous work either did direct lifting, which is of course very hard, or did coarse to fine refinement, which this is as well. But here our intermediate representation is actually implicit and not explicit. So we don't have already a hand here that then through computation you refine.
You have this privileged access to most people.
Right. And what is interesting, so we do make a point in this paper that you can think of this as actually a conditional prior on the scene. And what we then actually do is we sample based on the prior points. And then what we do is we have a transformer that uses the sample points and then looks up image features, and along the way, even with cross attention between the hand and the object, refines its predictions. So I think it's actually an interesting algorithm, and maybe the best way to think about it is you have this conditional density estimation here, and then it's almost like a Monte Carlo conditional algorithm. Which is, yeah. But let's don't get stuck here too much. The point I was making now is really, in this critique of pure vision, a different way to study sensory systems is through this goal-driven approach. And there are many papers for many different sensory systems, and this approach is successful. And of course, also like any other approach has many problems. And so one thing that I did want to talk about today, of course, is how we did this for proprioception. So for studying the sense of location. This is actually work that builds on an earlier study that I did with Mackenzie in human, for modeling human proprioception. And then we extended it with two of my grad students, Alberto and Alessandro, and Axel Bisi, who was a master student and now is a grad student somewhere else in UFL. So imagine you hike down a very steep trail. Okay? Then vision, as we all know, after this week is relatively slow. And you need to know where your center of mass is. So if you hike down a very steep trail and you don't really know where your center of mass is, and it's slippery or it's dusty and therefore actually quite slippery, it's very dangerous if you do not know where your parts of your body are. And so that with that steep sucker in the middle there, in the middle of falling, looks like resting. Okay, resting. I had a different picture where Steve Zucker looks in a more precarious posture, but I didn't want to show it. Anyway, so yes, proprioception is essential around here in Telluride. And so what is proprioception? Just to remind everyone, it's the sense of posture. It's basically the sense that tells you where your body is in space if you're not looking. Okay. How does it work? It has, so basically, there are multiple sensors distributed in our body, in our skin, in tendons and joints, and in muscles that give distributed and partial information about the state of the body. That information goes to the spinal cord, from there to the brainstem, thalamus, and then cortex. There is a parallel pathway that I'm not talking about. This is, let's say, the pathway that would be involved with the perceptual aspect. So if I ask you, well, where's your hand in space, and move it around, and you tell me, then it will be biocortex, most likely. Now, while I do highlight that there are multiple sensors, the most important sensor we know for doing this are so-called muscle spindles. And muscle spindles are really fascinating neurons. In my mind, some of the most fascinating neurons in the body. So they're called muscle spindles because they literally have afferents that wrap around the muscles, okay? So if you have a skeletal muscle, there's a capsule. Inside this capsules, there are different fibers. And then there's some combination of afferents that wraps in certain ways around these fibers. It's not important for this talk. And through this, so what they then sense is physical properties of these fibers. And then there's, of course, some mechanical transduction that goes into these afferents. And then different afferents, they will actually, okay, the textbook view is that they report the length, velocity, and force of multiple fibers, essentially. Yep. And now, so this is at the input to the proprioceptive system. If you go up the hierarchy, there are all kinds of interesting tuning curves. In the interest of time, I don't want to explain this figure, but let's say proprioception in higher areas, you can find tuning to direction, to specific postures, to velocity, to acceleration. So the question we were asking in this work is, what is the integrative logic of proprioception? Okay, and the logic or the motivation is the following. Imagine you have an arm and you move it through space. Then you could hypothetically, and this is actually a simulation, record what all the muscle fibers send you as information. And what the brain really needs to do is, well, for you, it would be easy if you get that information to know what your arm is doing. For you looking at these patterns, I don't think it's apparent what is actually happening. But the brain or the proprioceptive pathway really needs to answer this question, well, what is the trajectory of my limb? And as a matter of fact, here, the limb is actually tracing out an A, okay? And so the argument that we put forward in the paper is that, that the body and the brain co-evolved. So if we were to create synthetic data based on the biomechanical system, well, I should say, it's very hard to actually record from many spindles in real data or in a real organism and then actually create such a model. So what we argue is we can use models of muscle spindles and we can use models of biomechanics to create the sensory statistics or putative sensory statistics that goes into the system. And then we can optimize neural networks to do various tasks based on these statistics. And we can check, well, do they learn the right inductive biases so that then they can explain us something about the neural code. Okay, that's the basic idea. So it's very similar to the work I was talking about earlier, but of course in vision, I mean, you could just go out there and there are tons of pictures on the internet. In proprioception, there's not tons of data on proprioception on the internet, number one. And number two, it's hard to even record. So we argue that biomechanical models are a good way to get it. So we had this work that was recently published. So the goal is to reverse engineer proprioception. And as I said, there are really three ingredients. First ingredient is we simulate muscle spindle dynamics at scale. Notice, so this is actually, so we do this in macaques because then we can do brain recordings later and compare it to the brain recordings. So here we use a biomechanical model of the macaque arm. So we create such a large scale stimulus space. Then we simple sample some ANNs. We train them on various putative goals that people have argued the proprioceptive system is actually optimized for. And then once we train our models, and only then, we actually go to the experiment of the monkey. We have a monkey doing a sent out rich task. You've seen this task before in this week. And there's actually back to 3D. So we can infer from the 3D movement of the monkey's arm, the putative muscle states in its arm, and then feed this into a frozen neural network model. We extract the latents at different layers, and then from there, we regress against neurons in the brainstem of the monkey and neurons that are recorded in somatosensory cortex. And of course, and I should emphasize that only at that step, we use real data from the monkey and real movement from the monkey. Our putative models are purely trained on synthetic movement data. Okay?
How do you train the parameters so we get biomechanical model?
Okay, so we don't, because there are because basically biomechanical models for macaques, this one in particular, it's Moran and Schwartz ARM 2006. I don't know how much. It's a reasonable model for the macaque arm. Yes. So there are, and that's, remember my title, biomechanical simulators. There are biomechanical simulators that people have worked with. It's actually specifically is an OpenSim, which is kind of the leading simulator for biomechanics. And we rely on that to create the synthetic data. Yes. And of course, every biomechanical model has some differences to reality, but it's a reasonable one.
So just make sure I understand. So then you take the biomechanics simulate, and then you essentially pass that through a bunch of experimentally
No, we directly regress against neurons. So we don't even try to look for tuning curves in our network. We literally just, for the actual movement that the monkey makes, we extract the latents at a particular stage, and then we linearly regress against the real dynamics of a neuron. I'll show that.
Give them a couple of these objectives to most reach.
Yes, that comes. Good prediction. So first part, creating the candidate models. What we do is, because we only model the arm, shoulder is of course fixed. We calculate which points in space can you actually reach, so the attainable kind of manifold. And then there we impose various movements. As a matter of fact, we actually did impose character drawing. Which,
What question?
Yeah.
I think there's one there.
Yes. Oh, sorry. Thank you. Sorry.
going to ask, why do you need a task-driven paradigm here? Like, couldn't you just look at specialists?
Yes, great. There will be tasks that are purely information theoretic. And we will compare it to those tasks as well.
And yeah, I want to back out. So in terms of biomedical model, I believe that will have people done basically modeling of humans using GMG, like it should be GMG throughout. That's it.
Yeah, I guess in a very simplified answer, that's what biomechanics has been doing for 50 years. Now, like people build these biomechanical models, they measure skeletons, where the muscles are, then they try to infer, well, yeah, with EMG, if you do inverse dynamics to actually activate the right muscles, it's of course overactivated and complete, and so it's not straightforward to actually invert that process. Not just if I observe your kinematics, it's not straightforward to say which muscle activation gave rise to it, because it's actually complete. Yeah. But in a nutshell, that's really what biomechanics has been doing for a long time. And there are also many open questions. But for simplicity, let's say we have a pipeline to do this. And then we use neural network models. And for simplicity, we just use TCNs, temporal convolutional networks, and recurrent neural networks. So now what computational tasks did we actually consider? And here we considered 16. So let's start with the information theoretic ones. Basically, we had two unsupervised tasks. One which is an autoencoder, where the idea is, in some sense, you could argue that's pure proprioception. The goal of proprioception is to reconstruct the complete state of your muscles. That's a form of pure proprioception. An alternative is Barlow-style redundancy reduction, where the argument is, okay, just like in the optic nerve, I mean, you have a constraint. The spinal cord, same thing. There's clearly a constraint, and you probably want to remove redundancy along that pathway. So what we did is we implemented a redundancy reduction algorithm. So these two are unsupervised algorithms. Then there are 12 hypotheses that are actually supervised. And those would be more aligned with what the textbook tells. So if you do open the Candel book, Fundamentals of Neuroscience, it would tell you that that's the role of proprioception. And that's also how I introduced proprioception. I said, well, we think proprioception tells you where your body is in space. Now, of course, the question is, in which coordinate framework? You could pick many different ones. So, for example, you could have egocentric Cartesian coordinates,
think only of your hand. There are actually people that do think it's just that. You could have egocentric coordinates of all your joints. You could have actually, for example, coordinates that are just angles, okay? Joint angles. And you could imagine many, many more, but whatever, we did 16. So for those different coordinate frameworks, we could argue, well, maybe the only thing that proprioception extracts is the position of the limb, or just the velocity, or position and velocity, or position, velocity, and acceleration. Okay? So this combinatorically, as you can imagine, you can come up with many, many tasks. So then I'm left with two other ones. This one is the action recognition hypothesis, which is kind of the equivalent of object recognition. So here you would not know where is my arm in space, but what is my arm doing? Okay. And then this one is an interesting one. And I should emphasize that for simplicity and to isolate proprioception, we only modeled passive movement. So in some sense, we're not modeling motor controls here, where this agent is moving its own arm. We're modeling that someone would move your arm. Okay? And I can give you many reasons later why there's this first step that makes a lot of sense. And one hypothesis that we do use, and it is a sensorimotor hypothesis, is because we are passively moving this arm around, we could, of course, predict what torque you need in order to go to the next step. So we calculate that. And then we do train the model to predict the torque in order to go to the next goal. So then you, And as you can imagine, for doing these different tasks, there are actually different decoders in order to train those tasks. So what we do to compare all the tasks is we pick a particular encoder, and then depending on the task, we put on like the right decoder. We enter and train it. And now for testing the proprioceptive system, we throw away the decoder because that's task specific. And we compare these encoders. Okay. And so, for example, in torque case, we actually have another input here that conditions on what the next target direction is. Okay. So these are our 16 tasks, and we can train candidate models. And now, and notice again, we only train on synthetic passive data. But now we have data of a monkey doing a scent outreach task. Here's a video. And because we have 3D deep blood cuts, we can, of course, infer the most likely state of the muscles from this video. Okay. And what I also want to emphasize is we actually have two states, two different conditions. So the monkey reaches to 8 different directions in a cued way with a screen. These are active reaches. So notice here the monkey is really driving the arm. Okay. And then there's something that is actually passive perturbations, where the monkey is between trials in some sense, and the monkey doesn't expect this, but it will be kicked randomly in a direction. Of course, these movements are relatively slow, and that's fine. Well, slow in the sense that you can take multiple seconds into account because the monkey controls that movement. Here, we only take the very beginning of a passive perturbation because, of course, after some time, the monkey will know how it's being perturbed, and this information will be reflected in the neural code. And for that reason, we only take the first 90 milliseconds. So we take advantage of the fact that there are latencies exist to gain insight into passive perception. Okay. So now, okay, you wonder, well, how well does this actually work? Notice that unlike in this vision work I was talking about, what we do want to explain is we want to explain the neural dynamics over time on a single trial basis. And so what I'm showing you now is our best neuron, a neuron we can explain best. So each section here is a trial for that neuron. It's actually a brainstem neuron. And in black, you see the firing rate of that neuron over time. This is roughly 500 milliseconds, so the monkey actively moves. And the arrow underneath indicates the direction of movement that the monkey had. And I want to highlight, the fit from our model is the red one. And notice our model has, of course, not seen this specific trials of the monkey doing this. And it can really capture the neural dynamics. And again, the model is there's 2 going down. Yes, there's actually 3. And that's different areas. Yes. And so this is actually, that was one of the most exciting things for me, because there are 3 that go to 5 o'clock. And notice that the firing is actually quite different. And if someone would have shown me this neuron, then I would have thought, well, it's probably the monkey's in a different state and whatever. But what this shows is that the postural information itself and inferring the state of the muscle, plus perhaps correctly integrating the muscle information can capture the differences in these different trials, which is nice, no? Because that means it's purely visual, it's purely sensory, this information.
So just to be clear, in these 3 trials, the monkeys, like the state of the arm was different before that you do in all 3,
Even during. So what we do take into account is the complete movement. And I don't know which 3 trials this corresponds to, no, but it's some of those trajectories, and they're slightly different in space. And the posture of the animal is actually perhaps slightly different. I mean, the elbow is, it doesn't make sense, but I think it's nice how how good this is actually to explain the data.
what part of the brain studies is.
QNet nucleus, which is the first area that receives proprioceptive input. Okay, so this works well. So this is the same figure that you just saw. This is for active, this is for passive. So here time is much shorter. Oh, sorry, I was wrong. It's 130 milliseconds, the first 130 milliseconds. And the same model can explain both the active and the passive. And this is cortex. And in cortex as well, this is again our best unit. We can reasonably capture the neural dynamics.
Question of the model curves are plotting, those are a regression showing your models accepting to its actual on some cell training.
Yeah, that's testing.
Okay.
Yeah, this is testing. And I should emphasize, we do one linear readout across time. So the weights of our linear readout don't change across time. So the dynamics really has to be captured by the neural network itself. Yes. Okay, so now, of course, so now I showed you that this works on some best neurons, hand-picked neurons if you want. But of course, this is with Utah arrays, so there are multiple neurons recorded. What we can do is we can average over all neurons that are recorded. And in that way, now we can do comparisons across models, tasks, and so on. And so that's what happens from now on. So I will only have one explained variance number. And let me show a bunch of controls. The first one is, this is a distribution, it's a bit of a complex plot, but it's a distribution of neural network models that we trained. And it is how much better is the neural network model than explaining the neural data than a linear model based on the muscle information itself. Keep in mind, linear model based on the muscle information is not that trivial because we actually have 39 muscles. So in other words, the input is 80-dimensional. So this is a powerful linear model. But usually, on average, we beat it by 20%, and in the best case, by 40%. Then, remember when we talked about the untrained CNNs? You can, of course, ask the same question. Is task training even important? Can I just randomly do a kernel trick, get some filters? And task training does improve the performance a bit. But of course, this gain is less than over a linear model. And here is another control, which is, well, you could say, okay, but in order to explain the neural code, you're actually now using a very powerful nonlinear method. What if you would just, on the training set, train your model to fit the data? That would be a data-driven network model with many layers. And here is data-driven performance versus task-driven performance. And data-driven is substantially worse than task-driven. Okay. Yeah. So in other words, and I think that's cool, no? Because that means, well, we can, with synthetic data that we simulate ourselves, tweak our model to have better inductive biases, and then explain the neural data to some degree. But this statement that I just made is has even a radial information. So let's focus on one particular task. It's hand position and velocity reconstruction. And what we can, of course, do is we can compare many different neural network architectures. Okay. So it's a bit of a complicated plot. There's 6 colors. The different colors are different monkeys. These three guys are QNet nucleus. These 3 guys are S1. And on the x-axis is, so each dot is a different neural network. So different encoder, inductive bias. And on the x-axis is how well does the neural network solve the task of inferring where the hand position and velocity is in space after training. And of course, you can imagine that some models are better at doing this than others.
What does the usually different neural network?
Different neural networks, like more layers.
More layers.
Like they use like wider journals, like that kind of thing. Like just, yeah. And actually 350 models that we trained in each case.
So in other words, this axis is purely optimized on the body, if you want, on synthetic data. And this axis is how well does it generalize to explaining information in the brain of the monkey. And we find correlation in all of the cases. So in other words, if you're better at solving the task on the synthetic data, you're better at generalizing to the monkey, which is nice because that suggests that we're perhaps optimizing the right thing.
Isn't it worse? Because
Oh, MSE, because MSE is how you're better at localizing your hand if MSE is lower. No, because it means perhaps if you over here, this is actually, you have 1 millimeter accuracy of localizing your hand. Sure.
The effect is not overwhelming, right? Right?
The what?
This effect is not very large. It's a little bit better.
It's significant, and yes. Yes, and I think one of the reasons why this is also the case now is if you correct, depending on the deductive bias, your model might just out of the gate be already much better at doing this task. That's one of the reasons why maybe it's not the strongest. So better. Anyway, so that's comparing on the same task, different architectures. But what we can also do is we can compare different hypotheses, try to tackle the question of what hypothesis best explains spoke research.
So it's this stupid experiment with the model that you have like a system for some very large dimensional space of muscle positioning. That's your input.
Yep.
The network. And then you're trying to predict the task.
Yep. So as a figure here, so it's actually TCNs. So either, let's say, spatial temporal convolutional networks, then, first spatial across muscles, then temporal, or 2D convolutions on the muscle time pattern stacked, or temporal spatial. So these are just different factorizations of the same thing. And then we also have recurrent neural networks.
What is the spatial?
Well, it's muscles, essentially. And in that sense, this is a very poor inductive bias because using a CNN across muscles is nonsensical.
Right.
To be fair.
That you don't have enough which muscles are next to one another.
And we have, in the meantime, of course, built models where we do this, but in this paper, it's machine learning inspired inductive bias. Okay. It's a convenient architecture, but it's not a particularly brain inspired architecture. But okay.
Yeah, so what are the 6 colors again?
Different monkeys.
Different monkeys.
Yeah. No, there's 2 monkeys. Not a 6. There's 6. Oh, yeah. Okay. This is monkey C1H and S1L. So these are different monkeys, different probes in one session.
As you have multiple neurons per monkey.
Yes. Between 20 and 100. So 7. Okay. But now, of course, what we also want to do is we want to compare tasks. And here, as you can see here, the variability of a particular architecture is actually quite high. No, even on the same task. When you make the same plot with untrained neural networks, you still get a correlation. Fun fact. If you align it on how good it will it be after you train it on the task. And in order to take out that architecture bias, what we actually did is we take the explained variance of a model and we subtract the explained variance of its untrained initialization. And all the 16 tasks, we actually always train each architecture on the same initialization. So we can nicely compare all of them. And so when we do this, and when we then cluster the models, we actually got 5 clusters. And we color here, so this is a low dimensional embedding of how much better are you than an untrained model. And the coloring of these different groups here is according to how much better are you. I think there's an animation. This is for John. These are untrained. No, you're as good as randomly initialized. Here you're getting better than randomly initialized, and here you get worse. Now, of course, the question is, can we label this by task?
And that's for the network. This is for the models, the neural network models what you.
Yes.
Yeah.
And so here we compare the tasks themselves, and we try to factorize out the bias of the architecture. Yeah. So now comes a cool result, I think, which is our best cluster is models that are trained at predicting the position and velocity of the body, but irrespective of the coordinate framework. So you can do joint angle regression, or you can do egocentric Cartesian. Your model is equally good at explaining the product. And I think that's cool because in the 80s, as maybe some of you remember, there were all these arguments about, well, what is the coordinate framework of S1 or Actually, QNet nucleus no one asked because no one had recorded before we never recorded this data. That's like it.
Like in relation to what though? Like it's better to predict position and velocity. I don't know what the symbols speak, but position, velocity, and what?
Okay. So remember that basically each dot now is a group of neural networks, and here we can compare all the tasks. And so better than, for example, randomly initializing your neural network. So this is really hypothesis comparison, this big. And so the best cluster is you train on position and velocity, irrespective of coordinate framework. And now notice if you train on only position or only velocity, that's the second best cluster. But it actually has less explained variance than if you train on both jointly. Okay. Then the torque and autoencoding is as bad as randomly initializing your neural network, which is curious. And redundancy reduction, sorry for Horace Barlow, is the worst task by far. And then there was
Any acceleration that does.
yes.
Wow.
Yes.
Can you
So,
explain that?
yeah, so that's an interesting point. No, in the machine learning sense, if you do multitask training, you get a better representation than if you do single or fewer tasks. So why don't we get a better representation if we also train on acceleration than if we leave it out? That's a curious result. I do think so the interpretation we have is, so there is acceleration tuning in S1 and QNet nucleus, but maybe in that task, it's not the most engaged. These neurons are not particularly engaged.
Also, acceleration in this task can be really noisy. So
That's exactly right. So it's really noisy. It's very hard. And actually, the spindle inputs that we use, we also didn't model force, just because it's passive movement and it's extremely hard to model force. We are, of course, working on this now. So in that sense, I do want to put an asterisk here and say that might be a limitation of the method so far and of the data.
Why is it particularly noisy in this task?
Well, because second derivative of any value is noisy.
Yeah, you're not actually, you don't have an accelerometer, so you're not.
Like you need the task, but you turn around.
Yeah.
That's right. So it's a limitation of the data itself and many others.
Alex, in the vision part of your talk, you emphasized how you have made real progress on reconstructing the hand by having this implicit, surprising representation.
Right.
And here you're using explicit variables of the sort that, well, have been around for a while. Did you get any insight into?
I would love to, and we don't have any insight right now, but there's something we can about. This project started 3 years ago. Yeah, the project started out before CVPR, so.
So I mean, this is actually a really measure of like how trainable these different architectures are. So, I mean, presumably you could do the same analysis on just their absolute level of performance, and does it look the same? Or
Wait, so why do you, I mean, I do agree with you that the performance of an untrained model at explaining the neural data is actually correlated with how well it does after it's trained, which I think is literally a limitation of our optimization algorithms. And it's a machine learning problem. But here we keep in mind we factor that out as much as we can. So we subtract
I understand what we're doing that, but I mean, it seems like you'd also ask like, what's just the best model in terms of absolute performance? Is that like maybe that's more interesting?
Right. So we did try to do that. It just we couldn't get much sense out of, let's say, the inductive biases. Oh, I want to compare these muscles, integrate these three muscles in order to explain this neuron. And I think it will become clear in a second why that is the case. Because in fact, the interpretation we have in our paper turns everything I told you on its head in a second.
Okay, so actually,
Lee Carlo showed that they actually tried like dozens of different architectures.
Yes.
And people used ResNet, but in fact, over time, what they showed was that the explained variance kept going up, in an absolute sense.
Yeah, this is similar, but of course,
No, I think what you're doing is more informative. But what Michael was saying, that's already been done. That was actually the main goal for those people in the vision.
right. And it's interesting because, for example, transformers actually bucked the trend. So what Terry is referring to, if you look at ImageNet performance versus how well you explain IT, the performance actually went up until transformers led to the stage. You're better at ImageNet, but much worse at explaining neural data. And yeah, well, it's not a very good inductive bias for people missing. So, in fact, for example, DIT transformers don't even have test detectors on layer 1. Fun fact. Okay, so now I should say, so we have this clustering. We get a very similar clustering. This is for jointly clustering QNN and cortex, but it could be that either one of them actually likes different things. Turns out they don't. Now we do the clustering on passive data of the monkey, okay? So remember, we actually have our synthetic data is passive data. This here is the passive case where the monkey is randomly kicked around. When we do this, we end up with 2 clusters, and in the better cluster is not so much improvement over just randomly integrating muscle information. There's a little bit of improvement, but it's not that high. And that's a curious fact that goes to something that I will tell you in a second. The second curious fact is, of course, we know anatomically that QNN nucleus is 2 synapses away from spindles, and S1 is 2 synapses, well, depending on what neuron, but give or take 2 synapses away from QNN nucleus. So we would expect that our models, earlier layers, just like in vision, should better explain QNN nucleus, and late layers should better explain S1. And it's not true. It's always the late layers that best explain both QNN nucleus and S1. And as a matter of fact, the best task is predicting position and velocity. Now, if you're 2 synapses away from muscles, and we do actually know how many muscles a QNN nucleus neuron integrates, it's not many, then it's odd to predict the position and velocity of your limb from the muscles. Because it's odd in the sense it's the non-trivial calculation. Which is why we argue in the paper that what we're actually showing is that QNN nucleus and S1 are modulated by top-down information of the efferent's copy of motor cortex. And that even in QNN nucleus, even though it's very early in the hierarchy, the best latent at explaining the neural data is actually where your body is in space in Cartesian or joint angle coordinates. And it's not in muscle coordinates. And that I think is very interesting with respect to our control theoretic arguments, because if you're moving yourself, you recode very quickly into very useful coordinates, and you no longer operate in muscle coordinates, is what this suggests. Now, why?
Wow. Okay. Yeah, you said it. I like it.
Yeah, and
It's really interesting.
And that's why in the passive case, where there's obviously no efferent's copy and you don't know where you will be, for example, the model that is trying to predict position and velocities is better than random, but not much. And so what we really think is happening here is, okay, we modeled the proprioceptive passive system passively, and we isolated proprioception. But then what we actually find is suggestion that they're very strong top-down modulations. And of course, we're now very actively going after this.
So there was some guy, 1887.
So predicted this? Well, okay. This paper is actually a really exciting paper for anyone interested in the muscle sense. In this paper, Charlton Bastien, I guess his expression, discussed at that time, they weren't really sure. They didn't know what the sensor of the body is and how body state estimation worked. And they called it muscle sense. Some people and others thought it's all top down. So there was actually an argument whether everything comes from efferent's copy or whether there are sensors that tell you where the body is. And of course, this is a joke that I made myself, because as you guys all know this famous quote, though. So this says, there are things in the mind that are not prior in the senses, which of course, no, the interpretation here is your proprioceptive pathway actually has representation if you actively move it that is not from your senses. And as continental European, I do like that. Saying this here, empirical Americans.
How early does it happen that you get muscle and the small station is left?
Yeah, and I don't want to push too hard on that statement, no, but it does seem
Push hard.
Well, it's two layers in, no? And in QNet nucleus, the best way to explain the population activity has this problem.
Now, I do want to say something which is very curious, and I showed you the muscle spindles. Turns out muscle spindles are the only receptor in the body that actually receives central feedback. So there's the gamma motor neurons that actually, you could talk about this for a while, but actually the way the sensing works is the extrafusal and intrafusal fibers, and only extrafusal fibers produce force, and they're actually driven by alpha motor neurons, the thing we usually talk about. The spindles, they wrap around intrafusal fibers, which are not force producing, and they have their own motor neurons, gamma motor neurons, and it's believed that they actually involved in, compensating for delays and so on. So one of my favorite hypotheses about all of this is that it's not up here, that it's maybe even cortex controlling the muscle spindle directly in active movement, and that is why you leave muscle coordinates very early. But I have no evidence for this whatsoever. So I think it's my favorite hypothesis.
So it was one inside the journey.
It's a protection. That's right.
So the modulation is mechanical because you're driving the tension of the fiber.
Right.
It's beautiful.
That looks like my slide lux. I mean,
yes,
that's amazing. I had no idea anybody. That's that. But it's not the only receptor that has feedback central. It's hair cells are modulated by inputs from centrals, descending central input.
but isn't it?
I'm sure. So no, it's a huge part of the way that you regulate the dynamic range, for example.
What?
Yeah, the outer.
Oh, yeah, the outer hair cells. Okay, only one class.
Right. Yeah, I'm good. Well,
And then what is interesting, by the way, about gamma as well is, so gamma, fish, for example, don't have gamma. Creatures with limbs, we're getting far away from the central line.
But by the way, it's true that our retina doesn't have feedback from the cortex, but birds. The birds have to. They do.
Because they evolved from a blind shrew, so birds have feedback and have way better vision.
Yes.
Well, good question.
Where does the cerebellum fit in?
No, look, this is purely modeling proprioception. No, it's only modeling the cortical pathway.
That's all.
So right now, this picture it doesn't. And in the interest of time, maybe let's talk later about it. I don't know how much time do I have.
You're up.
I have a completely second part, which is how to learn to control items bodies. Well, I don't have time. But bottom line is, complete RL is a good way to do it with policy gradient methods. And you all know about this, that this has come on stage in the last 10 years. And the policy gradient methods actually work extremely well. But you all also know that there's a huge gap between what we can do in control, especially of morphologies with RL, and what biological systems can do. And here's even some English guy that made it to the final. There's an enormous gap, and I think it's an interesting question. What is actually missing? What is missing in RL to close that gap? And I made a discussion slide, I think. And I wonder what people think is actually missing to close the gap. Of course, one thing that came up a lot this week was internal models and model-based control. I think three other ones that partially were also, especially this one was discussed, inductive biases is a very good one. I think there's a lot of we can do for better exploration, and curriculum learning, I think, is also a key thing. Cognition, one fact is, even though, let's say, RL is really powerful optimization algorithm, one of the issues we have in practice is, well, we don't know the reward function. That maybe the brain has worse optimization, but better reward functions, and that's actually what makes it work. Okay, so time's up, but I don't, okay, that's a real thing. Because I wanted to talk about those three things: inductive bias, better exploration, learning. So let me just do it super quick. Inductive biases came out beautifully this week. I really recommend this paper by Tony Zahner. It's a critique of pure learning and what artificial neural networks can learn from animal brains. And of course, the argument in that paper is, well, that the brain out of the gate is not a random ANN that is trained on tasks. It actually is highly structured. Okay. And we had a paper in NeurIPS 2 years ago where we took very loose inspiration from the sensorimotor system and how it's wired up. And we actually have a GPT-0 architecture because So firstly, we have independent temporal processing for each proprioceptive pathway. And then we have a single layer attention where you can basically dynamically gauge how that information flows to independent controllers. And what we show in that paper is that with this inductive bias, you can learn to do motor control with a changing body without ever telling your controller that the body is changing. Okay. And it's because the inductive bias basically takes care of it along the way.
This is a mixture of experts.
It is a mixture of absolutely, yeah, absolutely. Yes. And yeah, and so that's of course, and the other thing I want to highlight is this better exploration aspect. Again, this is by two grad students at Darren, who was an undergrad and is now at Harvard. And what I want to highlight here is actually something that I think is quite interesting. If you take policy gradient methods, I think most of you know, in a nutshell, you have your sensory input, you want to predict an output, and in order to train this neural network, what you actually do is you create state action pair rollouts. And while you create those rollouts, you actually add IID Gaussian noise here. Well, and then you use the state action pair rollouts to calculate the reward function and update, or take the gradient and update the neural network. Yep. We argued in the paper that, so, and for many, and you can get very good performance, especially in low dimensional bodies, or in general, this is a very good method. But imagine if the dimensionality of your body gets very high dimensional, or if you're planned, why would you do IID Gaussian noise here? Doesn't seem like a good strategy, no. And that was the point of our paper, where we made the following argument. How can we deviate very simply from IID noise? We could say, well, even if we don't learn some complicated covariance matrix or whatever, we could do the following. We just say, well, look, we have a policy network, and implicitly, the penultimate layer has some information about the structure of the body. So if we actually not injecting IID noise here, but if we're injecting IID noise here, then we bias it according to some of the logic of the body. And the idea is as simple as this, and it's Gaussian Europe's. And we can beat SAC, that's right, and we should beat PPO. Okay, so even on smaller bodies, low dimensional bodies, there's really no change, honestly, in performance. But for example, for the humanoid, we almost get 2x more performance with this very simple trick. But now I'm not really interested in these kind of.
By the way, this is a little bit like dropout.
I don't think.
No, when the idea is that during training, you're in that case you inject the noise by getting rid of the canceling on. In this case, you're adding noise, which is a little bit like.
I don't think it's different because here, keep in mind the covariance structure of your noise that you integrate is actually is according to this W. So you have structural noise.
No, it's selective drop.
Right. And I think what is interesting about this paper, honestly, we still haven't found a single paper where someone did full covariance. We have someone gave noise at the level of a full covariance matrix. People always do diagonal matrices in RL, which seems actually of course makes sense because it's a lot of it. But the thing we were interested in particular is controlling muscles, so very high dimensional systems. Here we're controlling 39 degrees of freedom, and this is early training. This is late in training, and the task is, of course, to rotate this object to the target direction. And Lattice, the algorithm that we made, can do this really well. You can also take this pen task where you need to rotate pen to a particular orientation. And again, this is a very challenging task. You're controlling 39 muscles in a biomechanics simulator, and you need to manipulate this object. And what we showed in the paper is that we can beat, let's say, PPO, depending on the benchmark, by quite a substantial margin with this very simple trick. And PPO is kind of a state-of-the-art RL. Yeah. And another thing that is actually nice is that Lattice learns energy-efficient solutions. So if you integrate over the torques, you can, of course, calculate how much signal do I send, or how much energy do I send to my muscles. And intuitively, it makes sense, no? Because if you do understand that you don't want to, at the same time, drive two flexors, because it's not, that you don't want to drive an agonist and an antagonist at the same time, when you explore, that's in some sense the idea of lattice. You also end up at the end with control policies that are more efficient and that don't have that much co-activation. So we not only get more reward, but you also have less energy costs for the pulse.
But we do code the traction. We're learning something new.
Yes. And it really depends on the task, if you want to produce forces or whatever. But here you need to produce forces. You don't need to.
After you do something well trained like a tenniser, then you're not doing code the traction. Right. It's less energy.
Right. And so I talked about inductive biases and how maybe better exploration methods can also help us learn better. And in closing, okay, give me, I don't know how much.
Like in 10 minutes we have another talk because some people might.
Let's stop you. But bottom line, if you want to win a competition, you don't win it with any of you need all these things, but you do need to take inspiration from humans. And our inspiration is actually this kind of skilled art. And so we wanted to win this benchmark, this endurance challenge for rotating 2 balls in your hand. And the inspiration we took is from how athletes actually learn skills. And so what we came up with was a specific curriculum learning policy that is basically graduate students trained. But you should think of the graduate student more like a sports coach that coaches your RL algorithm to win the competition. And so we want that competition win. And here I do want to highlight, remember, biomechanical simulators. This is now no longer an OpenSim, the previous simulator that I showed, but this is in Myo Suite, which was initially developed by Meta. And we trained our curriculum learning policy for more than 400 hours on a single GPU. It's curriculum learning, you cannot really parallelize it. And this simulator is maybe 1,000 times faster than OpenSim. So 400 hours times 1,000 is longer than the lifetime of my laboratory. So I think it would have been hard to convince grad students to work on this. So here is that I think one thing that is exciting right now, these biomechanical simulators are so fast that we can study very interesting things about biological motor control. And in closing, so we won the competition. And then what we actually did is we looked at how the control policy does it, and it arrives at a very similar low-dimensional structure manifold as Todorov measured when we let people do bounding balls in the laboratory. So our policy finds 5 degrees of freedom for bounding, and in his experiment, he found that people use 5 degrees. And now I cannot talk about all these other things. I think that's it. Thank you. Thanks to my lab. Sorry for no well shot.
Yeah, it wasn't much arm twisting. It was just a question of getting the invitation. But
That's what you get for not showing up for a couple of years. But anyway, so just to put it in context, these guys were talking about 1985 back in here, and you guys all know what has happened since then.
I mean, it's the lowest point on that graph.
I'll get to it. I'll get to it. But yeah. People like this go back with the show. Just be patient. So from 1985 to about 2012, we were doubling the amount of compute that we use to train networks every 2 years, which is the rate at which Moore's law improves the technology. And after people figured out how to do this on a GPU, which you saw earlier, I think Terry described, and that is we started doubling the amount of compute every 4 months. And now you've got with these language models, you're doubling every 2 months. That's 12 times faster than Moore's law. And so GPT-3 run like almost 10,000 GPUs for 2 weeks all out. Use cluster of 4.6 million. And it basically, the carbon footprint was about 1,300 cars for 2 weeks, running for 2 weeks. Now, Google's, data centers, the amount of energy they are using has gone up like 0.4 times in 10 years. And so that's where we are. And this is just GPT-3, right? You're going to hear more. It's still going, right? And I want to give for myself in this time scale, right? Like Andreas and Terry said, we all met at Hopkins back in the 80s. And Terry introduced me to the elegance of neural networks. And Andreas introduced me to the elegance of analog VMs. And these influences were decisive in my trajectory. He basically set the path that I was on. And so from there, I went to do a PhD at Caltech in the 90s, 90 to 86. And that's a picture. You can see some of the people here. Chichi, and you can see Andres, who was visiting at that time. This was about 96. And my advisor was Calvin, who was no stranger to this audience. And then from there, I went to Penn. I was on the faculty at Penn for like 8 years before moving to Stanford, 6. I'm putting this information there for the younger guys. People ask me how I got to be where I am. So, but that's my treasury. This CNS program is a computation and neural systems program, which was relatively new in those days. In fact, I did it to CS.
It was the first one.
Yes, exactly. I was admitted to CS and then I transitioned to CNS after the started program. And this was really a great program which trained you both in the neurobiology and in the technology. And so you see that imprint of my trajectory. And so I got there in 1990. And in 1989, this book came out. I don't know if you guys signed neural systems. And in 1990, he published this paper called Neuromorphic Electronic Systems. And this is a quote: the brain is a factor of 1 billion more efficient than our present digital technology. They're a factor of 10 billion more efficient than the best digital technology we got now. So at the end of Moore's law, back in the mid 2000s, all that improvement will still leave us. Yeah. And why was he talking about these factors? There was an implicit assumption that the scaling is linear. In other words, if it's this much energy per operation, well, if we build a bigger system, the energy of procreation would still be the same. So it was just factor was a gap. And it's taking me like 30 years to test this assumption. Okay. And in fact, it's common folklore among engineers, people who build computers, as you scale out these systems, when you go from the chip to the board, it's of 10 more energy costs per operation to communicate. When you go from the board to the server, it's another factor of that. When you go from the server to the rack to the data center. And so it's obvious as you go to engineers, as you scale out, that the energy per operation goes up, right? And so I said, just about 5 years ago during COVID, I said, okay, so we actually had that same problem, right? And if so, by the way, so these are the numbers, the 6 others of magnitude up so. So to figure this out, whether as we scale out, the energy per operation is going to stay constant, for the whole system energy or not, you have to actually lay out the network so that you can measure how fast signals have to travel, you can compute the energy, and so on and so forth, because it's basically the communication cost that's going up with scale. And so, so this is your 10 layers deep, 10 neurons wide, deep neural network. And you basically, what you do is you come in with your 10 inputs, you have your weight matrix. You guys know all of this. And those weights in that 10 by 10 matrix weight the inputs, and then you sum them, and then you threshold. And that's your normal neural network layer. And then you basically have to sense all these signals, not just to the next layer, but to other layers and so on and so forth. And I think Michael wasn't here, but you guys send that signal to the challenges, so that's a fire. Part of the brain has to the final box. And even in these modern transformer networks, there's like, decoder and encoder will get feedback and so forth. So you always have some number of signals that have to go along with it. Okay. And that's the guys who cost you steps of energy. It's okay, because you can implement this local 10 by 10, matrix vector multiply very efficiently with a crossbar, which you've seen here, where these local connections correspond to this wet line that's running this way. So that's the activations from the previous layer. The weighting is done by the memory cell, like a memristor or a floating gate transistor. And the results of those weighted inputs are currents that are summed on the bitline. Right, so we were building this Jen House again was building this back in '92 in Tyler's lab. And so you have one of these crossbars with each of those weight matrices, right? And then you have to interconnect them. So these purple lights here at the interconnect, they correspond to these global projections. And so if you were to do this in a 2D chip, you have to basically kind of like use another layer of wiring for your interconnects and then another layer of wires going that way. So and you end up with wires that are lining about 100 neurons wide. And if you basically generalize this to a network with n neurons that are in layers squared of n neurons wide, and they're squared of n of those layers, you end up with wires that are running order n stiff. And so you've got a bigger network that's sending more signals, and those signals are traveling longer distance, right? So both of those things are scaling with the number of neurons, and the energy is proportional to the distance. And so you end up with energy scaling quadratically in your number of neurons. Okay. So that factor that we talked about is going up as there's not a constant factor in a bigger network. The energy per inference or the energy per operation is more expensive.
So, if you apply this, a very nice way to quantify and the scaling to the brains, what do you think?
I'll show you. Okay. You'll be blown up. Well, obviously, if you look at the brain, right, people actually measure it from a 7 million neuron mouse brain to an 86 billion human brain. The number of neurons, how the energy per unit time, which is measured in glucose consumption scales, and it's linear. It's not correct. Okay. So the brain has figured out a way to run these long distance connections all the way to the thalamus for everybody in such a way that we are not scaling quadratic. It has to build a bigger brain.
Well, what's the slope?
It's 1 in the microbes. This is log scale, so it's log. Yeah, exactly. And this book is a fantastic book. You read about scaling brain bonds, brain architectures, and all that, with lots of data on different. Okay, so now, if the brain scaled quadratically instead of linearly, a fly brain will use as much energy as a human brain. Right? You take Susanna's data, you extrapolate it to 1 neuron, you change the slope to 2, and you end up with 25 watts being consumed by a brain with 250 neurons. Okay, so that's the difference the exponent makes. Okay, now nobody wants to build a fly brain. We want to build a human brain. So we did that. We went the other direction where we said, okay, what is it going to cost us to build a human brain if we're scaling quadratically? It's 3 terawatts. That's the entire American energy consumption for the real.
So my directed argument for the handing basically is the argument that we made a leading question to first, that we don't want just a full crossbar to do everything. We actually want things to be much more local and sparse. But just the same way that things got saved from doing FPGAs.
Yeah, but even if in that case, I don't have a full crossbar to it. Each neuron is just doing spirit of injection. But it's the way you tell, if you tell those crossbars, you have squared of in up there, then a signal that wants to go to any crossbar every going out of land, that's going to scale. It could be only one guy you want to talk to, another club. But that crossbar is at some arbitrary location. Right. Exactly. It's like an axon in the cortex may make 10,000 synapses, but it has to go down to the thalamus and make a couple of synapses, and length of that wire, that energy is more than all the synapses it makes in the cortex.
I think that's absolutely fair. I would second like just from this thing with like FPGAs and stuff like that. They quickly got away from doing broad, just straight crossbars because they knew they were going to die.
Yeah, but that's what I'm saying. I'm not saying how to like.
No, it's like, but so I'm just saying that there's not. I'm pretty sure that.
I'll show you the opportunity.
And also, I can agree that doing weights or scale something makes a real stuff. It really doesn't make sense.
Yeah, but it's even better than going to multiple racks and then all that. Right? It's even more expensive, right? Yeah. Yeah, but this is just showing you, I'm going to say, like, basically the goal is to get linear scale like the brain bits. And I'm going to give you a recipe for doing this, which also makes predictions about maybe how the brain achieves, right? And I'm going to try and, then pull out the implications of that, both on the biology side and on the engineering side. Okay. But yeah, there's more clever things you could do, but, it's not going to get you to read. Okay.
So, so in this case, so I mean, just to put it in context, you know, that's why these guys are talking about building $100 billion Stargate AI supercomputer, which is going to have millions of GPUs, and it's going to burn 5 gigawatts for the next, you know, beyond ChatGPT. You know, we need a power plant. The nuclear power plant is 1 gigawatt. So they're also looking at getting like 5 nuclear power plants to make this happen. Okay, yeah. So, and you know, whether they have brain scale or not, I think there's still like a factor of 100 to 1,000 brain scale in terms of number of parameters. If you say the number of synapses, thanks to electricity, is the number of parameters. And so we are seeing this play out. And Carver was preaching, you know, now everybody talks about energy efficiency, but he was talking about that back in the team. Like, okay, we saw this come. Okay, so how can you reduce that export? You can reduce it to a power of 1.5 by stacking crossbars. So you go 3D and you stack those 10 crossbars correctly. And now, it's just to remind you. Oh, was there a question? Or somebody unmuted his mic here. So now your web lines, which correspond to these local connections, are still here in the crossbar, and your memory cells and your bit lines, which are summing sort of being weighted. Those are your dot products. But now your interconnects can just run vertically across the stack. And so the distance for a signal from one crossbar to go into any other crossbar is on the order of, you know, square root of n instead of n, right? And in fact, in technology, it becomes just 10 microns or something to go across several things. You see it. And so now what you find is that now you're, if you basically some fraction of these neurons in each layer, you have some activity fraction alpha, then out of those square root of n neurons in this layer, alpha can square root of n sensing. You basically have to compute how much wiring you charge that, and that would be your energy and inputs, right?
And this one we see more of flash.
Exactly. Yeah. We'll get into it. Yeah, but we're not using it to do neural networks yet. We are getting there. But I think we should, that's one of the big points we should. But anyway, so basically you can just calculate the volume of this cube and multiply by alpha. That's the amount of wiring you have to drive, and your energy will go up accordingly. So this is n to the 3 half, you go square down by square root of n. And so your energy is going to scale like n. It's like 3 hash. So let's see how much better off we are doing it. And so now we scaled with it power 1.5, which is this line here, so 1.5. For 25 watts, which is what the human brain consumes, we'll get 60 million neuron brain. And that's like a lizard's brain. Okay, and if we extrapolate the other direction, okay, so where we're going with a slope of 1.5 now, that's 10 megawatts. We add about it initially. So by going 3D, you can really have a big impact. This is now, it was a factor of 10 to the 11, now it's a factor of 10 to the 5, 10 to the 6. Okay, but we are still way from that point. And we still haven't found a way to this. Okay, but there's actually a more fundamental problem. Anybody know what that is? We got 3D, we stack all the star heaps. Exactly, the heat, yes. So how does that work, right? So now you've got this same picture here, the same as before, but now your area is going like, you know, it's sub-zero at square root of n by square root of n. So your area is going like n, plus your volume is generating heat is going like into the 3 halves. So area is scaling square root of n slower than the volume, which means that you have to be at a higher and higher temperature to use Newton's law of cooling, which means that the thing is going to fry. Okay, and so any 3D computer faces this problem, and the brain has the same problem. It's a 3D, and you got to get heat out to the surface area, to the neck, something that's proportional to. It's going like quadratically, But was there a question?
No, that you have all the stack of wires, which actually help you.
Exactly. So that's the thing. You actually reduce the energy per signal by square root of n, but you reduce the area even more, because your area before that was like n by n squared. You know, your area is like n, right? So you're more efficient, but you're not efficient. You don't reduce the heat sufficiently, right? So you have to do something else. So what is that? Blood vessels. That's like water cooling in the computer. It still has the diameter can't continue to increase the blood. It has to go to the nest. That's correct.
It's not human. It's start thinking about neurons. Less utilization, sparsity.
Sparsity. Exactly. Okay. You have to be sparse. Somebody did the other work. Okay. And how sparse, everybody says there should go with sparsity, but I'm going to tell you there's an actual target you have to hit just to be thermally viable. And that also seems to be what the brain is doing. Okay. So what you do, so you go from this model here where some fixed fraction of the neurons are signaling every inference of a unit time to this model here where there's a fixed number of signals in each layer, which means that the fraction of neurons that signal as the layer gets wider is decreasing. Okay, if you do that, you can already see that I've reduced my activity by a factor of square root of n. That's going to take my energy, that is the operation now, by a factor of square root of n. And that's going to not only keep me, so now my energy is getting like n, which is like my surface area, so I stay cool. And I get that linear skin that the brain has. What's T? What's capital B? It's just a fixed number of signals per layer. We'll get into it later. The degree of sparseness. The degree of sparseness. The degree of sparseness is d over square root of n. It's going down as you build a bigger brain. So like a human brain has to have more sparsity than like a mouse brain, because the surface area to volume ratio in a human brain is less than what don't you make degree of occupancy first? Activity. So yeah, active. Exactly. This is exactly. So this is like basically I think a vision that has not any signals and inference in each layout stage in the time. So it's activity sparse.
And I want to connect to something that silicon people. So what I might say, we shouldn't be worrying about dark silicon, because the field that's clearing is basically our dark silicon.
Yeah, in the wires are just sitting here, they are not going any part. It's like, so yeah. But
Nice, still, right?
yeah, they do.
Upset.
Yeah, yeah, that's like a fabrication cost skin. Yeah. Still gonna come back to this. Yes. And this is exactly how FPGAs handle this conversation. They build their cross-bar networks entirely so that way they the exact same kind of scaling behaviors by sparsity. So I think it's beautiful. But let's just be aware that there's actually more arguments in your favor to make this happen. Yeah, I would say that in an FPGA, typically when you implement electronic circuits, you have a fan out by a fan in from 4 to 6. In the brain, that connectivity is like 10 knobs. That's actually so we'll get into it. Yeah, but yeah, so I think it's a trying to map this kind of network onto is an entirely different scale of problem. And so this is kind of the proposal. So let me just try and summarize this, because this is sort of the first part of the talk, and these are the key take-home points. Or you can think of these as these are principles of skin neuromorphic systems, or even the brain, right? So what I've argued, or what I'm arguing here is you organize your neurons in groups. You can call those groups layers or columns if you're in the brain, and you connect them densely locally, but sparsely globally. And this is very sparse because, you could make square root of n connections within that column, and then you could make one connection, some arbitrary and so on, right? So that it's got that sparse connectivity as well. It's not just, but yet you still, because this, global connection is so expensive, you still have to use activity sparsity.
What's pretty interesting from the start, point one, is that's basically mixture of experts. You've got these sub-networks.
Yeah.
Erasing the trade one. So
yeah. So it's actually, so these guys are onto it. They are starting to get much more sparsity in these, language models and these image expert models. And that's actually very unlike the traditional rail use where the activity, I'll get into that next when it comes to sort of a coding thing, right? And there's also information here I can make as to like what the limit is, right? And I'll get into that. But, so. Yeah.
we have a mixture of experts with one million experts talking with here today.
Okay. Yeah. Yeah. What time?
It's one that we swapped with this time slot. So we don't know.
Yeah. Okay. I got that one. Nice. Yeah. Okay. Then, you're going to increase the neurons in the group by square root of n. I mean, you could do something different, but I'm saying these proportions work. And then you're going to decrease the fraction that signal per inference like 1 over square root.
right? And then you are going to have to build this in 3D. I'm like, you're not going to get that. That's a big part. Those connections, you have to shorten those connections. And if you do this, then the whole thing works. You get a linear scale with family scale. Right. So the question then comes, which Jason alluded to, is that is this degree of sparsity achievable, right? This is saying there should be a constant number of signals in inference no matter how wide the number of keys. And so from that, you can make sort of, it's not information theoretic is still fancy. You can just make a counting argument, right? And the counting argument is as follows, is that actually the number of signals you need, it shows that the number of signals you need that are necessary are one per intrinsic dimension. This has come up a couple of times because we were talking about manifolds, right? And so this is like a data set that lives on this Swiss law manifold. And you would say that the dimensionality of the input space is 3D, which means that each data point has 3 coordinates. But because it lives on the Swiss row, we'll say that the intrinsic dimensionality is actually 2. Basically, if you take any point, there's only 2 directions in which you see other points. You don't see points in the third direction, right? And so you can do this empirically. You can measure this for like a data set like ImageNet, which appears each of those images has 150,000 values, the pixels and the RGB, those pixels. And so then each of these points now live in this 150,000 image states. Each one is an image. When I actually go and you look on an image and you look around it, how many directions do you see out of images? You can just do this empirically by like putting a ball at that point and expanding it out. And the number of points that you hit will increase like out the dimensionality of the highest, because that's where the points are. And you do this for ImageNet, it's about 35. So there's only 35 directions in this 150,000 dimension space where you see other images. And so once I'm on the manifold, I really only have to specify 35 values to tell you that's language. Okay? Yeah. And so that basically is the number of signals that necessary, the minimum you could get away with. And what about language models? Because we're talking about that, right? So GPT-3, and these numbers are these papers. GPT-3 is sending around these 12,000 embedding vectors, which means that each word or token lives in the 12,000 space. So if you can plot those vectors, you can find those points, and you can do the same thing. And what you find is only in 10 directions you see other words or tokens. So instead of sending 12,000 signals around, you could be sending 10 if you are moving on the map. Okay. And so we're going to, yes.
Doesn't it matter to how you organize the database? The database organization is sure.
Yeah, you mean the representation, like how you represent the information is key, right? And so kind of like that's a learning or representation learning problem, or a data fold and manifold unfolding problem that's about full inference. Yeah, manifold inference, exactly. Yeah. And so this is the kind of thing that Steve is into. It's not easy, but people are doing it.
But there's measurements of the size of the manifold during cognitive tasks in mice, and it turns out to be about 5.
Yeah, exactly. You see that in brain data too, I guess, Mark, because it's not here, but yeah. So yeah, exactly. So you had someone.
Why do you say you need one signal per dimension here?
Because it's kind of like, think about the Swiss roll version, right? Think about the Swiss roll version. It's like if I wanted to tell you a particular point on the Swiss roll, a particular data point, I just say go along the Swiss roll up to here, and then go across it up to here. Those are the 2 signals I give.
Coordinates.
Exactly.
Or relative coordinates.
So they are coordinates along the map.
They're coordinates of the tangent plane treating that at that point. And in the interesting directions move on that tangent plane, rather than all around the circle, are in principal directions. So they're going to be orthogonal to each other, and then they don't vary depending on.
Yeah, where you are, right? Yeah. There's a metric tensor.
So yes, things know that the manifolds are continuous.
That's good. Yeah, and the same dimension,
And this because then where
Yeah. So some places, like he described, Steve described manifold here which was what you call it, not pure. Right?
Non-pure.
Yeah, yeah. So we are talking about pure manifold. Impure. Yeah. And so
That's a different problem.
yeah. So, but you know, but there's a more fundamental point I'm trying to make here, right? Which I haven't made here, which is that these numbers are a property of the data set. They are not a property of the network. So when you go from GPT to GPT-4, or you go from ImageNet to like some more higher resolution images and all this kind of stuff, that intrinsic dimensionality doesn't change. It was just like how Steve was saying, he collects more data. It doesn't, it's saying he just fills out this, right?
So
And so,
that would be true for I can see for image, but I'm not sure I can see the ChatGPT. I mean, you say ChatGPT would be type.
I mean, people have done it for 2 and 3. We haven't done it for 4 yet. Maybe, I mean, this was back in 2021, maybe, yeah. But they haven't seen an increase. Yeah.
So what was your point of that?
So my point is that, so this number of signals that you need doesn't depend on how wide or how deep your network is. So in principle, you could keep the number of signals fixed because that's remaining to data set like, you know, yeah, it's the task, right? And so the kind of sparsity that I'm prescribing is actually achievable, right? You know, if you can hit that, you know, necessary, you can hit that minimum point. So we don't know whether this number of signals is sufficient. We know it's necessary, right? And so does that make sense? Yeah. Okay.
What assumptions you make about signals like fire?
No. It's got to be solid. So it doesn't tell you how far. It's like a coordinate. Right? It doesn't tell you how far to go in its direct.
But aren't you leaving out all the work to get into that manifold?
I am. Yeah. I am. I mean, people have sort of looked at it and these sort of deviate on their way. They sort of unfold the manifold as you go in, and eventually they get into sort of this sort of Euclidean like thing. And so, but I'll not get into that history because energy. So, but let's say, yeah, there's some early layers that have to do this, but generally those early layers, like if they are like convolutional and things are local, then they are not that expensive when you get into the fully the stuff. If you're not unfolded by the time you get there, then you can do this fast. But this is just sort of first principles kinds of thing, just to see, you know, what the constraints are. And so I'm going to try and synthesize a code that achieves this law, okay? So I'm going to say I'm on a manifold that's intrinsic dimension 3, and I'm going to sort of partition this particular part of the manifold as I put neurons down, right? So, you know, if I have one neuron and I set its weight vector with its bias, that corresponds to some plane with a setting orientation and a setting translation in the space. So this neuron will, I mean, it's like a ReLU model here. You know, will respond to all data points on this side, but not on that side. So it partitions the image space. And then I can put on the next guy, and I can put it, I'm constructing this, but if you do it randomly, orientations and biases, you get the same scaling. So I'll give you the references for that. I put the second one, I can double the number of partitions. I put the third one, I can double again. Now I try to put the fourth. There's no way I can put the fourth plane such that it intersects all of 8 that I have now. Best I can do maybe something like that. And so I split 4 of them, and I get 4 more partitions. And so then once I exceed the number of dimensions, okay, and add more neurons, I'm getting this sort of diminishing effect. I'm not really going to give you the formula, right? And that's how it goes. And the way it's scaling is that when your neurons are less than the number of, the number of neurons you have is less than the intrinsic image size, 3, you can scale exponentially. But once you exceed, your number of neurons exceeds the intrinsic dimensionality of the manifold, you scale like the number of neurons divided by the dimensions raised to the dimension. So it's exponential in the intrinsic dimensionality, not in the number of neurons. And so this is also telling you something about the coding you want to use. Like if you're up here, you could use a binary code. By the way, I'm just telling you this number of bits is just counting the number of partitions. Okay. So in a different partition, when you cross this, some neuron comes on and some neuron turns on. Pattern of activity changes. Okay, so that's a different patterns you can cut. And then it's going much more slow. And so what does this mean, right? This is like you're using a byte. Each neuron is putting out a bit, right? Because you need n bits to the end to count. Here, it's like So what's happening? It's like you have D signals or D symbols chosen from N over D symbols, right? So you've got a number system with the base like N over D, right? Instead of 2. And the number of digits in that number system is like G. Okay, so that's like scaling like the number of digits you need. It goes like the number of dimensions, not like theorems. Okay, so how could you do something like that with spikes?
So this is very similar to the Shannon capacity for motion scan in the logs here.
Okay, but I thought that was signal to noise ratio. But this is just number of neurons.
So if I take log of this, just to pick on the
Yeah, exactly. Yeah, you can take a log of this and you get bits that you need to include.
yes.
Yeah, and if you do those bits in this base number, if you use this base, then you just need D of those bits. I mean, not bits anymore, bits. Yeah, so you can pick up that. But I don't want to get into that because they were funny. It's trying to coding. Very funny to do, right? But yeah, so I'm going to try and construct a code that, uses, can count this many, can distinguish all these partitions and use this kind of scale, right? And so imagine that the data point is here, right? I'm going to say, I'm not using real U anymore. I'm going to have a unit where, only the closest, the one whose plane is closest to the data point response, right? So in this case, in the X dimension, I'm closest this third unit. I mean, this plane 3 is closest, right? And then in the, the other dimension here, it's in the Y dimension, this third unit is also closest. And in the Z dimension, this first unit is closest.
Right.
So now I'm going to say, I'm going to have grouped these units that are linearly dependent, like they are coding the same direction together, right? And one of each group will find the guy who is closest to that plane. Okay? And so with this kind of code here, I can use 3 signals, which is like my intrinsic dimensionality, to count up to basically distinguish any of these.
To find that only that's second.
Yeah, I don't lose any information about which partition by just, setting this up. Yeah, that's yeah.
Can you explain why it has to be order?
Yeah, so the order tells you which dimension or which place the digit is, right? So I'm using like base 3 if you want to think of it that way. And the first place digit is this guy. He's the first, guy to find. So the order in the sequence is just telling you the place of that digit.
Right? Are you saying it's the same 3 guys?
Yeah, so any of these 3 guys respond, basically these guys are going to respond. Basically, we're going to take this, there's no sequencing in there, but we're going to order them such that this group goes first, this group goes second, and this group goes third. And so that corresponds to which dimensions that information, right? Or you can think of it as that these units compete among themselves. Basically, the units are competing among who's close. And then we need some ordering to tell which dimension.
Yeah, so I just want to say that this reminds me a little bit of the simplicial neural networks that Pedro, my colleague, where you basically project this the software and this simplicial that you use around ordering their models. So you really how to go and find that and use.
I have to move faster. No, sorry. Yeah. But anyways, but I mean, this is a simple construction. Right, and Johannes.
Just a better explain. So here in principle, just by reading on which neuron spike, you will already know where you are. So
Exactly.
But here there's not really any information encoded in the timing itself.
No.
I mean, it's just there.
Yeah, exactly. These are just places that you're filling.
Some delivering models.
Or like
The ordering is that
order.
exactly. Just
The
ordering
ordering
markers, not type.
Yes.
Order it.
Okay. And so now, okay, so this is what, people have talked about as sequence coding, right? And there's quite a bit of evidence going back to 1996, about, these hippocampal replay neuron running sequences. And, there's some recent results here from like Jill Loren and technical cortex, where, they stimulate a neuron and they see a sequence like this, right? And this is sort of some modeling work that reproduced Joe's results here, right? And so, we've heard a lot about this, Harry, about X-ray. There's less evidence about sequence decoding, which is that, okay, how would a downstream neuron detect, because we are paying, this sequence code, you have to pay attention to the order.
Could one think of this as packets?
Yes, you can think, I'm going to say, I call it the atom of information in the brain, right? It's not just a spike, it's some organization spikes. Yeah, okay. And so the evidence for sequence decoding is like more recent, right? Where there's this, I'll show you some data here from Ikigayer, where this is like a dendrite, you're looking at individual spines here. And what he finds is sort of an ex vivo slice of CA1 that you get spontaneously activated synaptic inputs, either sequentially like that towards the soma or away from the soma. Okay. And so this suggests that you're telling some pattern of spikes that was encoded into a synaptic sequence, as I like to call it. And this stretch of dendrite can discriminate that somehow, right, to detect that, right? And this is sort of the data, spontaneously, like, for example, these red guys, sometimes the order changes, but there's the strength where it goes from towards the super. And similarly for the blue guys.
Does it involve EPF things?
He's doing calcium imaging.
All right.
Yeah, so you can see sort of spine heads line up, and so and so, but it's hard. You can do this to slides in the future, right? And but powers of order, this here, so it gets similar result where he's decoding from the calcium activity in a short stretch of dendrite functional information about the task, the multimodal information of the task that the mouse is doing. Okay, so out of this, got me to propose sort of a novel conception of the learning brain, right? And the ideas are sports, right? We've had a lot about the synaptocentric. Basically, the idea, somebody asked earlier, is like, what is the fundamental units of information and computation in the brain, right? And the synaptocentric view, which goes back, 80, 90 years to Rosenblatt, and even before that, is this has now become sort of the idea that we, aggregate stuff spatially. That's a compute, this is this weighted sum. We take the non-negative part of that, and this is what GPUs, TPUs optimize, right? And the neuromorphic guys have gone with more of an exocentric, what I call an exocentric conception, where they are actually taking into account that we actually, spike. They use the rate or the timing, and they introduce some temporal primitives into the computation, right? And we've been doing these neuromonitors in 2D so far. And both of these, primitives and these encodings generate dense activity. And it's not compatible with the 3D, either the 3D brain or the 3D chips that we wanted to. And so the motivation came from there, and based on the evidence, I'm proposing this dendrocentric conception of the learning brain, where the information, the atom of information, is the spike, rank of a spike in a sequence. So there's some several patterns of spikes that appears in some population of neurons. They find some sequence, and where the spike occurs in the sequence is important. And to actually decode or detect this information, you somehow have to sort that spatial temporally. In other words, those red synapses coming onto that dendrite, those neurons fired in some pattern, but they connected themselves into that dendrite in an order such that you get the sequence. Okay, so that's some spatial temporal sorting. I'll get more into that. And I think this kind of coding has much higher coding capacity. In other words, with the same number of spikes, you can send a lot more messages by doing this. That allows you to have very fast signals. And that is compatible with 3D. Right now, everybody's talking about 3D, so they can go in 3D and so on and so forth, but nobody knows how to compute a file in a 3D chip because it's going to fudge. But the brain does that.
This related somewhat to the polygons, the polygonic network that Mr. Rich had proposed.
Yeah, so the polygons network is, he was saying that, arbitrary delays in your connection kind of rearrange the order in which spikes occur. And so you will get, even if they fire together, they'll come in a particular order. And he tries to sort of like use that again. But there's no, the downstream detector is not paying attention to that. It's just the delays have to give you a coincidence detection at the dendrite, right? Whereas I'm saying that actually it's more discriminatory to actually have a mechanism, because these things can overtake and undertake each other, and so they're going to summate somehow, right? So you get a much less precise detection. I'm saying I'm going to propose a mechanism within the QI where it senses the order, and so it's very selective. Okay, so we'll get into sort of how that's done biology and how you could do it technologically. Rough.
So, you might do a little bit of CDP except without the
Exactly.
like really profile.
It's very clear that the order is important, right? But we don't really use SD in that way because we don't have. Yeah, but I think this is compatible with that. Yeah.
I think we talked about this month ago, but this is pretty much what Kwabena is doing with this spike sequency.
Yes, so the governor in the area is only talking about these sort of special number of patterns. He had some models based on sort of calcium propagating down the dendrite and so on and so forth. It's still sort of finding a way to get delays to match up. And I'm moving away from that. I'm just saying, actually, we explicitly designed a structure that's detecting it. So you see, right? Okay, so let me move a little bit faster because time. And there's a bunch of stuff. So I sort of proposed this in this perspective that appeared like a year and a half ago. And I'm going to take you through some of those results and plus some new results. Okay, so those of you who have done your homework, you will get some bit of a exactly. Somebody's in there. Okay, so this is the idea. This is how you should start thinking on what's going on. You've got a pattern of spikes. You want to permeate it into a sequence, and then you want to detect. That is what I call synaptic sequence. You activate these synapses in the sequence. And so what happens is that these spikes are coming in. You are basically advancing a plateau potential along the dendrite. And if it crosses that stretch of dendrite, then you detected that particular species. Okay. And the way this will look like in the hardware is you need some kind of cross-file switching network to take some arbitrary pattern of pulses, connect them to the inputs of some sequence of the device, such that they become a sequence. And then this device has to be sensitive to the order in which it's active. And so I propose that could be done with a ferroelectric transistor. So we'll get more on that for the average folks. And I propose that this kind of sequence detection can be done with NMDA and KIR galvan beach channels in the spines. So we'll get into that. And so kind of the other part of this, so how do you learn this kind of representation or then to detect these things? Basically, you have to learn this permutation. And the most efficient way to do this is to sort spatial temper, which is the idea is that, you imagine that these axons are, going along some extracellular matrix. Okay, so this is an assert from development to happen over longest time scales, but that there's this extracellular matrix and the growth cone, which basically is the going end of the axon, follows the gradient and it gets to this intersection and it detects some gradient goes down. But the idea is that if the first axon goes that way, the next axon has to go this way. Okay, so just by the ordering, you're sorting them in time they arrive with this kind of structure.
Why does this happen in biology?
Here's how things get wired up during development.
Can you find the report somewhere?
No, that's how I can sort. So you can take axons and sort them so they arrive in the right order. Right? It's even before you make a synapse. Yeah, sorry.
But that's during development, not when the spike comes.
Exactly. So we're proposing that this is happening on a smaller scale in the mature structure. There's a lot of structural plasticity happening on short time scales where axons are growing out, and dendrites are growing to the podium, and axons are growing. Little branches and so forth. And you want
So this fragmentation approach implies that there is one optimal spike sequence that triggers something information rather than having alternative things being represented. Is that correct?
that would be the case, or like if these guys consistently fire in the same order, then that gets.
Kwabena, can I ask, is there a reason why it has to be through the routes rather than through having a diversity of different orders represented by lots and lots of
It's a good question.
style?
Yeah, so these are 8 neurons, so there's 8 factorial different orders that can happen. And so 8 factorial is like 10,000 or something. So you don't have space to put all those permutations.
No, I meant in the biology. I just
Yeah, the biology doesn't have space either. Your brain's completely full. They can actually can take one out.
Sure, I don't know. So, I mean, I might be joking a little bit, but, so what you're saying here, you can choose to solve not even update synaptic links, but just learn CPAPs.
I think, it's at 2 stages. It gets there. And then, depending, can I come back to that? That's okay, trying to come back to that. Yeah, so on the hardware side, there's various ways you can emulate this. But one of the, an elegant way to do this is with something called a sorting network. People build these networks, right? You give them a bunch of numbers and they come out sorted. Okay? Now you just give them a bunch of pulses. The first pulse got here, he comes out the first pulse, and so forth. And they compare the timing instead of the numbers, right? So you basically implement some kind of, switching network, which compares the time the falls arrives here and the time the falls here, and then it sets itself to swap to pass. And just by flowing through this thing, you'll get this starting of this.
Okay, let's see. I think that's
Yeah. So just to kind of get your ground. Okay. So now the last 2 things I want to talk about is elaborate on this idea on the detection side of things. I don't have much else to say about Reddit, right? Because I'm still trying to study that and figure it out. But I have more to say, and which goes beyond the perspective about how the biology could actually do this. And we are testing some of these ideas in collaboration with the collaborators. And but anyway, just to remind you, a spine, what those of you who don't know, this is a dendrite. The synapses are made onto a protrusion from the dendrite called spine, okay, and this is the neck. And then there's a protrusion from the axon called a bouton that is the other side, the release transfer out into this. And these are excitatory synapses, but they also contain inhibitory, I'll show you that. That's the GABA B. But and then, there's other synapses that are made onto the shaft, which are typically GABAergic. And so these synapses, this, everybody knows this alpine, this in MDA. Yeah, those are the excitatory glutamate binding synapses. And NMD has this voltage dependence, right? So when you are sitting near rest or hypopolarized, the channel is blocked by magnesium. You're going to depolarize it to open the channel, even though it's bound glutamate. And then eventually, because of the rest of, you're reducing the driving force for the rest opposition is here, the current goes, right? And KIR is just the opposite, right? So KIR sits there. This is KIR as well. It binds GABA, but it's voltage dependent, and it's blocked by magnesium on the other side. And so when you are depolarized, KIR is about the current, but if you're hypopolarized, you unblock it. And, then as you go down, you get current, it's flowing out. It's a potassium channel, right? So this is tending to reduce the voltage even more, and eventually you're going to go all the way here. Just like our NMDA can take you all the way here. That's called an NMDA spike or a plateau. And if you have KIR, you rest. Yes, potentially the rest. If you combine the 2, then you get this bistable system, which has 2 stable states and a threshold. That if you're able to cross, you go up here, and you cross, you go. This is in a single spine, but with bistable system. And about 30% of spines and cortex express both KIR alpha B and NMDA in the spine, which doesn't make any sense. But inhibition is supposed to cause an excitation, but it makes sense for trying to set up a side table. Just okay. So what happens if you take these spines? So this is just like a spine by itself, right? But what happens if you connect that spine to this shaft? You have other spines sitting here that are resting, and this guy tries to plateau. Then what happens is that the leakage, you try to increase the voltage here, you're going to some current is going to be drawn to the other, right? So that current is going to reduce your current, So this is the current you lost, and so you can destabilize the plateau. Yeah. So when you put these spines into a synapse for a large range of parameter values, which I'll show here, this is like Iris Mama, and we had a poster on this at the dendrites meeting. So here now I have the monostable system, right? Because my neighbors took all the current out and moved my, an MDA bomb down this way. So that's a subtle node application occurred. And so if you basically look at what different KIR and NMDA strands can give you that as a ratio of the conductors of the synapses to the conductance between the different spines, you find out that basically if NMDA is not too strong, you can get this to happen, the plateau will disappear. But when NMDA is about 10 times the conductance, your segment conductance between these two, the plateau persists. So there's a large range here where you can get the neighbors to destabilize. And you can also then know what happens when this neighbor plateaus, right? So in this case, this guy plateaued, and because now you're not losing half the current here, you can arrange things such that in that case, the bifurcation doesn't occur. Okay? So, or you restore the plateau. Okay, so you can have a situation where your neighbor plateaus, then you're bistable, but if that's whether your neighbors are at rest, you're monostable. Okay. The range over which you can get this, so when you're bistable, your energy diagram looks like this. The range over which you can get this, you know, this is NMDA, this is KIR. Over this whole range, you can get it. If NMDA is too small, you don't get the plateau because this bump is too small. And if KIR is too weak, then you destabilize this resting. So you're not, yeah. So if you have things set up like this, where you're in this range here, for both NMD and KIR, then you can get a situation that looks like this. So I have these two spines, and these inputs come in. If I hit the first guy first, move his voltage from here to here, it plateaus. Now I have a bistable system. And so when the second spike comes in, and uses AMPA to check about the thresholds, I can flip. Okay, but if I do it in the reverse order, where V2 comes in first, his neighbor hasn't flipped, so he's monostable. So he comes back down. And then when I hit the other synapse, I go here, I'm stuck here because there's no spike taking. Okay, so I stay at this. But with this mechanism, if you string these guys together, you can detect a sequence. Yeah, right? And so basically, you can feed these spikes into a structure like that. And as these spikes come in, you can get the spikes at plateau. And this is just zooming into that right here. But if you switch the order of two spikes, for example, this spike comes in here and this segment plateaus, and this spike comes in here. If you switch the order, then this switches guy with that, so that this you switch these two guys here. Then you get the exact same situation you see in this case. The I'm just shining since I just showed you the plateau halts, right? And it doesn't proc. And so there's a couple of more things you can say about this, right? And I can go quickly through this part, but this is the same plot here, which is showing spikes coming in here. Now this is space and that's time, and then this is a space-time plot of voltage, across the dendrite in this direction, and in time in that direction, right? And so as the spikes are coming in time, this spot has plateaued, and if this spike comes in next to the plateau, it continues to spread. And if you switch the order, it stops, just like I showed you before. And what we found is that actually you can get this to work with the smooth dendrite as well. But in this case, it only detects, the plateau holds only if you switch inputs that are 20 microns or more. So spines make the dendrite more selective to an sequence detection. Yes.
Kwabena, can you give us a stating argument how many synapses with dendrites?
That's why we're doing this experiment, right? So the question is how close can you put these things to discriminate sequence? And we are finding it's around 10 microns. So basically, if your sequence has 10 spikes, in about 100 microns of dendrite, you can detect that. So if you have a millimeter of dendrite, you can detect, 10 different.
So how many sequences can the brain store?
This is not about storing. This is about how much. This is a little bit like the context, right? This is a little like the context that the dendritic tree has, right? Because each of these plateaus to some state. And then, then the next thing can come into the next segment of dendrite, and that, you can detect that. It's like the context is how many things is to look at it over time before then it implies a spike. Yeah, exactly. And so kind of like the more dendritic tree you have, and maybe each every couple of tens of microns is detecting something, then that's the more things you can take into account before you this part is not a sequence.
Yes, I get holistic effects like a single spot. So would it also discriminate against like a case where you had, like say one spike happened twice?
Yes. Okay. So yeah. So those are like all excellent questions, right? If that has to do with a little bit like, okay, what would it tolerate if you get the second spike? For example, like if this spike that was swapped happens eventually, then like you saw in that case, it could flip and go. So if there are multiple spikes and so forth. So we are trying to understand the simple case before understand the complicated. But so I'm telling you kind of the stack. So this makes the other observation that's interesting here is that, young spines and young synapses are formed on longer spines, right? These are some example of spines here. And so what does that do to your sequence selectivity? It actually makes the dendrites, so it increases the length of these spines from 1.3 to 1.8 here. It becomes more tolerant to spikes. So before, this would halt the plateau, and now 10 microswat doesn't halt the plateau, but at 20 microswat depth. So this may enable the system to learn and refine its selectivity as it advances and the spines become shorter and more stubborn and so forth. So this is just for the biologists in here, that there are connections to these two things we know about how plasticity occurs. So now let's talk about how we can implement this in a device, right? And so what we proposed to do was to use something called a ferroelectric insulator. And this is the case where you have two electrodes and you have the ferroelectric material. It's called hafnium oxide, zirconium oxide in this case. And this creates charged dipoles where you have some plus charges and minus charges, and they can be, plus up, minus down, or they can be the other way around. And so you have this like stable system. And you can flip it just by applying a strong enough electric field to just flip the dipoles one way or the other. You do that by applying a voltage to the cake here. And so here is some example where they've measured this sort of double well potential, just like I showed you for the spider in this ferroelectric. And what we proposed to do was to instead of making a capacitor, we make the other side of the capacitor a transistor. And we string the transistors together, and this is worked out in collaboration with Smith Wong. Chen was the student who did that. And, what we've done, I'll show you some measurements. We showed that in this case, as these pulses come in, you flip the dipoles, and that basically lowers the threshold of the transistor so it turns on. And so you can see electrons are coming here. And then you can flip this one, and so once. But if you swap the first and second pulse here, and you try to flip these guys here, because these channels are off, you can't apply a voltage across that. And so you can't get a high electric field to flip that. Basically, there's no ground connection. And so basically, this guy doesn't flip, and then this guy flips, and that guy flips, but then the whole string comes out.
How wide is that channel? You get the isolation.
It's actually, that's a lithography fabrication problem. Yeah, it can be as short as you can make a transistor. But it doesn't have to, it's not relying on that. Just rely on the individual transistors. Functionally correct. Yeah. And so, but technically, this technology is not as mature as yeah, exactly. So that would be up to you wide if that was what you're asking. So we have 0.5 microns. And so this is like a wafer we got from Global Foundries, time system and Bayer. And, just to show you the cross section, these are your things. That's your gate stack with your ferroelectric insulator. And if we pulse 1, 2, 3, this is a 3-gate version of that device. At the end of the third pulse, we get the threshold is lowered, and now we get this current versus gate voltage. Right. You understand?
So actually using the polarization that it's set here to store kind of like the plateau.
Exactly. That's the corresponding. Okay. Where rest and plateau, it corresponds to dipole uptake.
And how long is that bridge there?
In this case, it's non-volatile. That's actually like a robotic this technology.
Okay, so here you can sequence that action only once.
You have to reset. Yeah, at the in the brain, yeah, exactly.
Exactly. You this on an land clutch.
Exactly. Yeah, but clutch is very different. But in principle, yeah, I'm sure that. And so, yeah. But if you basically swap 1 and 2, like you see here, you just get the threshold stay high, and you don't get your 10% first string. As far as they can measure that set. And so the whole goal here is to go and be able to do this in 3D because, like I said in the beginning, 3D is a big part of how you can get that linear step, right? And the memory guys basically started doing 3D back in 2007. By 2013, they had 24 layers. By 2020 or so, they had 96. And, this is what Shantanu was referring to. This whole stack is just 8 microns, right, to go up here. And, it's like these strings of transistors are like stacked vertically. So these are the gates, and they actually have some here. And this is the channel, and then there's just transistor along this macro. Okay. And so that's sort of like, us doing processing, we're still in 2D, and these guys, have gone beyond the 128 layers, they're now 232 layers.
Right.
And the density of these memory cells at that square millimeter is 18-fold more than the density of the number of synapses on that square millimeter. So, 3D technology has already gone and scaled way beyond the brain. If we can implement some of these ideas in this kind of technology, then, the future is bright. What I would say is that moving away from synaptocentric to dendrocentric learning would enable AI to run with megawatts in the cloud, So thank you.
I stop from the
I did that and I lost money. So I not necessarily.
But you should invest in Lloyd Watts. But so yeah, Chester means a great theory, and there is some evidence for synapses being close to each other, interact. So, but it would be fun, and there is actually an experiment was done at Geneva, the hippocampal slugs, in which what they did was they were able to use the light pulse to activate one spine and after that. Yeah, what they're able to show was that by doing a series of 6, they're able to reach threshold because active currents.
That's Michael House's. So Michael House's paper in 2010 about sequence discrimination and gender. Yeah, but this is I took that out. This was along like a basal dendrite over like, so instead of like 8 synapses, over some stretch of dendrite, they were using that, some part of the dendrite, use the whole long dendrite.
This was
Oh, I see a different bit. Okay.
It was a typical branch.
Oh, I see. Okay, then yeah, but that's exactly the kind of experiment you want to do. And, but the other thing with the Hauser experiment is that were they engaging?
No, this was.
He's in China.
Yeah, I think it's general reduction.
Okay, yeah, that's good. Because when you engage glutamate, the MNI glutamate actually, the MNI molecule that binds the glutamate actually blocks GABA. So people have done these kinds of experiments, but there's been a KIR, which is super steep in the game completely because it's shown in space stuff that of the deals. I think Shantanu had a question when he got it.
Yes, sir. Kwabena, can you comment about the learning part?
Yeah.
Learning combinatorial.
This is what I'm proposing the September one. If you do it the other way, it's going to become
Also,
you want to do it not with heavy and micro, you want to do it with like presynaptic elite.
also,
because then it becomes a sorting problem.
This is Hugo problem.
Yeah, and sorting can be done. It's not. Yeah, but if you search the space, it's going to be church.
also from the biomechanics, do we have evidence that this can be learned in a behaving animal or something? I mean, learning it.
So to test this kind of thing, which people are doing this now with like calcium images, but in people on the behaving animal, there's so much vibration, and you can't really track what's happening in the spine. They usually just record it on the software, right? And also calcium is slow. So you want to really be able to do voltage imaging, and you want to be able to do it such that you can track what's happening in the spine over the share microns, not just like a software. You want to see what's happening in that dendritic tree as they come in. What's happening? Yeah, and so kind of we are pushing towards there, but
Technology is not there yet.
it's close. It's getting close.
It might be worth thinking about development too.
Oh, I think about that a lot. Oh, and that's why I showed the growth codes slide and it shows so that it shows that on
Because
yeah, I agree.
that's when you have a lot of plasticity. It's when you're setting up this and threats.
Yeah, go ahead.
So you took us through the energy argument sort of to get to your device. can you take us back from the new device and what the extra infrastructure and the resetting and all of that, if you were to do something like that, you was at whatever process now do you imagine, how is that going to, because there are going to be trade-offs there, right? So the extra infrastructure is going to cost you something. Can you talk a little about that?
Yeah, well, she an engineer. You did very a lot of ideas. Yeah, I've kind of told you where I'm at, right? And I think those are like the next questions, right? So we've actually put out like some arrays now in global foundries. This is 28 nanometer process, but there's a lot of variability in these devices, so that's a challenge. We are looking at, as part of, Stanford now has this ME Commons hardware path, which is setting up to file collaboration. So like with Nickel Labs and these other, because the commercial guys are not going to explore this tricky routes. So you have to kind of like, work with like these more development fabs to do that. So we're looking at, the 3D track in that and so forth. So that's kind of like coming future work, yeah.
And the big group is one of the focuses really FIFETs to really send out a test chip by the end of in this technology by first week of September. So we'll be working on here to really do something with the help of Kwabena.
But it's really great that we have a commercial fab we can fab these devices. So we are putting out a chip to a 2D chip to do stuff like this.
I'm very happy to introduce you to Matej Hoffmann. He is the professor I'm collaborating with. He's in Prague and he's working a lot on embodiment, which I'm very interested in. So he will talking about closing the loop embodiment, active perception, and robotics. He worked a lot at ETH on this, so he will start talking on this, and I give you the stage, Matej.
Okay, great. Thanks, Julia. And yeah, sorry I cannot be physically with you guys there. I'm in Glasgow at the infancy meeting, so I do developmental robotics. So I'm interested in babies in development and how we can use baby humanoid robots to study that. And so I was asked to do like a primer kind of on embodiment and active perception. So yeah, so let's get to it. Yeah. Where I come from, so I did my PhD in Zurich with Rolf Pfeiffer, who is one of the he's like the Mr. Embodiment. And then I moved on to Genoa to work with this beautiful robot, the iCap, and since 2017 I'm back to Prague, which is my original hometown. And so this is my group. So Julia is now from June. Since June she's part of my group. This is our beautiful blue iCap. Okay, so this is kind of the only slide on what like the big part of my group is doing. So we study babies in their first year, like their sensorimotor development essentially. So for example, here we put like a buzzer, like a vibrotactile stimulus on their bodies, and we see what happens. And you see this kind of highly coordinated action, like bimanual action and looking. This is a 9-month-old. But it really takes those pretty much 9 months to reach for the stimulus on the elbow. And we would like to understand how come, what is the brain learning during that period. And so to understand that, we use this iCap humanoid robot that has whole body skin. And so we tickle it, and then you see it's reaching for the stimulus. And so this is an embodied computational model of what is happening in the baby. The caveat here is that basically we did this work 10 years ago while I was at IIT, and this is all programmed. So, engineers can solve this problem, but we believe that the brain solves this problem in very different ways. And that is basically now the challenge, that we want to get rid of all the engineered modules in the robot's head and replace it with something brain-like to understand, what the baby brain is going through. And at the same time, typically robots, you need to basically manually calibrate them and recalibrate them, and it's a lot of work needs to be invested into that. While obviously the baby can self-calibrate itself, and the brain is known to be very plastic, dealing with all kinds of distortions and changes. So yeah, so that's kind of the closing the loop inspiration from the babies to make better robots, and the other way around, robots as tools to understand infant development. Good. So regarding embodiment, so you guys are the neuromorphic or community, so something like brain-like. So I take it that you're focused on the brains. And in the first talk this morning, there was a mention of Eric Kandel. And so I'm gonna be a little bit provocative here. So this is a quote from this, Principles of Neuroscience book, that all behavior is a result of brain function. And so I do not agree with that. And so that's basically what this talk is mainly about. So behavior is not the result of only brain function for sure. And also perception is also not the result of only brain function. And so how come? So let's have a look at, what is the evolutionary origin of brains, or why don't plants have brains? So this is by Daniel Wolpert. Plants don't have brains because they don't have to move. Okay, so we don't have the brains for cognition or for perception. We have the brains to move. And so this is kind of a nice anecdotal example. There is this sea squirt that wanders through the sea, searching for a suitable rock to cling to and make its home for life. For this task, it has a rudimentary nervous system. When it finds its spot and takes root, it doesn't need its brain anymore, so it eats it. Okay, and then there is this, it's rather like getting tenure in academia. And right, so this, so this I think makes nicely the point. Okay, so I looked up a little bit, this space group at Telluride. I don't know, in the audience now, how many are actually from this group or from the other sub workshops, just to sort of see whom I'm talking to right now, and what it has to do with embodiment and active perception. So looking at this list of tasks, I'm just gonna, unfold the messages, which I will then explain in the rest of the short talk. So if you need collision avoidance, then you may not need to track objects or not track them precisely. You might use just much more simple means using the simple closed loop solution. I will talk a little bit about these Breitenberg vehicles later, so maybe that's relevant for these tasks. And then, so I've been a little bit exposed to your community. I was in Capocacha last year, and I know a little bit about event-based cameras, but my feeling is that you want to use them, you typically use them as, passive immobile sensors that are great at detecting moving objects, right? Which is great and it's very powerful, but that's not how biology works, right? Because we basically generate the events always actively by moving the body, by moving the eyes. And I think this is important that, that this next step is made, that, that the community is not scared to actually move the cameras and generate all the mess with all the unwanted events. But I think, that there is a lot of potential in that, and that might be relevant to some of the other tasks. And and also you should think always about embodiment, also where you place the camera, because that might basically be much more effective than the computation that you do afterwards. And right, so embodiment, trivially would be that intelligence requires a body, but it's more to it. So basically, there is this very complex interplay and task distribution between the brain, the body, the morphology, the shape, the materials, and the environment. So Rolf Pfeiffer, these are the books and then a science paper that so he was my mentor. So this primer is going to be based on a lot of his work. And so I claim that behavior is not in the brain, but it is in the interaction. And so this schematics is going to basically allow us to disentangle, the different loops. So here is the brain, here is the muscle or motor commands, here is the sensory feedback, but there is much more to it. There are internal loops. For example, there is this mechanical feedback loop that can generate behavior without even, the brain having a word. So I will show examples of that. There is also, feedback loops directly from the mechanical system to the sensory system, not going through the brain. And then there is also this external loop that the action that you take are going to really shape to structure the information that the brain will get back. And so this is called information self-structuring, and that can be quantified. Another related, let's say, concept to embodiment is this morphological computation. I don't like the word computation in this context very much. We wrote some time ago with Vincent Miller a kind of conceptual paper. So morphology can be used to facilitate control, that basically you don't need much of a brain if you get the morphology right to generate behavior. or to facilitate perception, like the insect eye, like the cochlea, or like the whiskers. They have particular properties. Or, you can, if you have a complex body, like a nonlinear dynamical system, it can be even used to do actual computation, but that I think is a kind of, border case. So, I would like to speak more about these, and this one is probably the most relevant for you guys. Okay, so the physical implications of embodiment is morphology facilitating control. So I guess many of you may have seen the passive dynamic walker. And so this is pure physics walking, okay? There is no brain, there is no motors, and there is no sensors, and yet it walks, right? And it's actually quite human-like. So this is quite impressive and quite beautiful. Of course, this is an extreme example. But it makes the point very nicely. There are other examples of the same kind. There is, for example, a dead trout body that can swim against the stream, upstream. And so here, there is no controller and no brain, no motors. We just have this mechanical feedback loop. And you may say, okay, the ecological niche is very narrow. So it is. But yet it can already self-stabilize, against some disturbances. Another example of this kind is this bicycle self-stability. So this guy will just propel the bike, and then he will even disturb it quite a bit, and it comes back. And this is this self-stabilization that can be quantified, for example, in Legit locomotion. And yeah, last example of this kind, if you want to do grasping, you may also be able to do it without any sensory feedback if you have the right morphology. So this is this coffee balloon gripper thing that basically can pick up any kind of object just by, so this is basically like there is ground coffee inside, and then there you create vacuum by basically sucking the air out as soon as you contact the object, and that it's just basically conform passively to the shape of the object. All right, so yeah, so this was kind of this kind of, so you see there is no sensing yet, right? So we can do all that without any sensors of any sort. Now, if we add some sensors, but primitive sensors, then you have these kind of creatures like the Gray Walter or Valentino Breitenberg vehicles. So this is actually in the pre-digital era. So Gray Walter was in the 40s. He was a neurologist, and then he built these beautiful tortoises that had a single brain of 2 neurons. Maybe it would be worthwhile for Telluride or for Capogacha to maybe rebuild it using brain scales. So they were analog creatures, and they could exhibit very lifelike behaviors like phototaxis or like obstacle avoidance, just by using these 2 neurons basically through the closed loop with the environment and through the body. So basically you can get a lot of complexity with a very, very primitive brain. And yeah, the same principle are these Breitenberg vehicles. This was called synthetic psychology. And so this was rebuilt in Lego Mindstorms here. And this is doing phototaxis. So it's this kind of vehicle. So if there is light on this photodiode, it will trigger this motor, generating the left turn and coming to the lamp. So here you already have the full thing, but note that the brain is really extremely primitive, right? You just have basically 2 one neuron feedback loops, and the sensory morphology, of course, can also do part of the job for you. And we know that there are these compound eyes of the insects, and every insect species has optimized the evolution, has optimized it for its behavior. Let's say, depends also whether it's a predatory animal. And one of the examples is that motion parallax involves a little bit of trigonometry, but for example, this eye of a fly has the non-uniform distribution of the facets such that it actually does the trigonometry just by that non-uniform distribution, and then basically you can it compensates for the sign relationship, and then just uniform motion detection circuitry will do the job for the fly, right? So it's simple, but it's effective. right? So we should always not forget that there is a lot of power that is in these things. So this principle of ecological balance means that the agent complexity, and importantly, its sensory motor and neural system, and the task environment complexity need to be in some sort of equilibrium. So, for example, if you have just one motor and one photodiode, you don't need much of a brain. If you just put a gigantic brain, it's not gonna expand what you can do. And if you put a high resolution camera and still you are here with the one wheel, it's not really gonna expand the action possibilities of the organism, right? So these are examples of that are not ecologically balanced. And yeah, here are just some cartoons. The going to the active vision. So active vision, active perception. Of course, there's literature on that. So I'm gonna cite Kwabena Boahen, who is our collaborator, but there is also, of course, work from Ruzhena Baichi, for example, and from Dana Ballard. So this theory of Kwabena Boahen and Alva Noy states that that vision and visual consciousness is essentially an active kind of phenomenon. So it's not that we're building that internal representation and we're filling in for the blind spot and for all kinds of nasty things about our visual apparatus, but instead it's an active process where the eye moves or the hand moves, and what the brain is picking up are just these relationships, the motor and its sensory consequence. So perception is knowledge of the lawful relations between actions and resulting changes in the patterns of sensory stimulation. Right? And it is only available through action. So this is kind of an extreme view or extreme point, but I think this largely holds for biological perception. And so, for example, here in this example is on the retina, if there is a straight line, if it's in the middle of the retina, it looks like this. But if it's like not in the middle of the retina, if it's more above, the activation would look like this, right? So it's actually not a straight line in that sense, but the lawful relationships, like if I move my eye left, what will happen to the image on the retina, that will still hold. So the fact that this is curved doesn't actually matter, right? So in this view, it's not a problem that you need to compensate for or anything. And so these information flows in sensorimotor networks can be mapped, can be quantified using information theoretic methods. So, for example, this paper by Lungarella and Sporns, they tried different robots, and they contrasted also different sensory morphologies, and they also contrasted different behaviors. So, if there is foveation behavior, like the robot following this orange ball, or if there is random behavior, random movement of the head with the camera, then this gives rise to completely different information content that you can compute on what comes into the retina, right? So if you do the foveation, so you do active vision, there is much more information content in the foveal area as opposed to the random, right? Which is not surprising, but again, this kind of makes the point, quantifies nicely the point. So I'm aware of some works in your community that close the loop and that do active perception, but I think that still the main part of the community is not doing that, and so I want to just make the point that I think there is a lot of potential in adding these closed loop approaches to what you're doing. And yeah, this is the project that Julia can tell you more about, that she just started in Prague, where the idea is that we do object recognition in the iCap using this kind of active sensorimotor contingency framework, where either the iCap will move the eyes or it will have an object in its hand and move it in the hand, just like babies do. And then we will compare different ways of doing the object discrimination or recognition using also spiking neural networks and with event-based cameras. So that's Julia's project. And so coming back to the messages, I think that the closed loop solution, you should not forget that that there is always this closed loop. And that the camera can be moved, and I know it will generate a lot of events, but I think that it will be meaningful events. But so I think this is a challenge that should be taken up. And yeah, take always the morphology of your robot agent and your sensors, including your camera, into account. And that's it. So yeah, thank you very much.
More people are coming. That was meant to only take 10 minutes. Okay. Yeah. Complex model. Okay, so let's start. Hello everyone. My name is Owen. I'm a research scientist at DeepMind, not Google DeepMind. One thing I learned from working at DeepMind is that large models are very expensive, and I didn't really like that, so I decided to study why they're so expensive. So I looked into the internal structure of transformer. I was thinking, okay, where do all these parameters go? I mean, they're large, right? And where do you spend all your flops? It turns out, like, if you know the internal structure, you have these blocks that you repeat for L layers, and then in each block you have multi-head attention and feed forward. I think it's standard now. Most of you already know this. It turns out that 2/3 of the parameters are in the feed forward layer. And if you look at the flops distribution, the majority of the flops are spent also for the computation of the feed forward layer. And as you're scaling up your model size, this proportion grows.
So that's basically the fully connected network?
Yeah, the fully connected network.
Okay,
Yeah.
that's it, yeah.
So then I thought, okay, if I want to make them more efficient, or at least understand how to make them cheaper, I should look at the feed-forward layer first.
So what is the feed-forward layer? The vanilla version, I think most of you are familiar with, is just multi-layer perceptual, where you have this input hidden states, which has like D dimension, and you project up to the feed-forward model. Usually the standard now is 4 times the model, and then you project back. So write this into a metric form. It looks like this, where alpha is a nonlinearity you choose. Could be value, sigmoid, or whatever. I think value is extract back again. And if you look at the individual neurons, you could see that this is basically a weighted sum of the value vectors, which is the output weights. So if I look at this in details, I would say almost all feed-forward layers, including the recent variations, fall into this unified framework, where from the input layer, you project into each of the hidden neurons, and I'm going to call this incoming weights WI, and this gives you the activation. And then you have this outgoing weights VI, which I'll call value vectors. And then additionally, you could also have a gate. So then what you get at the output has this weighted sum of value vector form. Now, if you look closely, this part, which I call activation, has exactly the same form as gating scores, right? So which one should be the activation? Which one should be gating scored? I would, by my definition, I would call the one that have higher sparsity and cheaper to compute the gating score. So what happens is that in this feed-forward layer, you have a lot of sparsity, either coming from the gating score or the activation. And those are zeros, so you could actually skip the computation of the value vectors. But so there are papers showing that, for example, you could look at individual neurons in the feed-forward layer, and they actually memorize specific knowledge, like what is capital of Ireland. And once you identify those neurons, you could edit them. So you could either delete that knowledge by removing this neuron or replace it by other vectors to modify the knowledge. But you're doing computation, like, so let's say this is the neuron for capital of Ireland is Dublin. You don't need this information most of the time, but you're still paying the cost because you're multiplying all these gators and activations. Even though the result is 0, you're spending flops on them.
What is the dimensionality of I?
Of Y?
I.
Of I.
Yeah.
So it's 4 times the model. So if your D model is okay, it's 4 times. It's 8 count. Yeah.
So let's look at some other type of feedforward backward. So there's so now this default model is a gated linear unit variation of feedforward linear. So in addition to activation, you have gating scores, and your activations are actually linear. So there's no nonlinearity, but in addition, you have a sparse gator that try to gate it. It's not cheaper, but in experiments, they have shown that this perform better. So you're adding gator here just for the sake of performance, not for efficiency. In addition, you also have this mixture of experts where you're adding, so instead of have one MLP, you're having, let's say, 4 MLPs, and each of them is associated with a gator. So all these neurons in one MLP is sharing the same gating score. The advantage of this is that you could skip all the other neurons that you don't use. So you're only paying the cost of this one that's selected by your router or gating score. Typically, the operation you do on the gator is a top K, which you select the most relevant expert, and then you do a softmax to sum up the contribution of each expert. Another version is this so-called product key memory, which doesn't have a activation, only a gator. So what they are trying to do is to select from a large reservoir of value vectors which ones should be combined to form the output value. So these vectors form a knowledge base, and then you just try to retrieve from it. They use a specific structure of a key matrix called product key, which I will go into details later. But the advantage of this is that you can scale to a very large number of DFF, up to 1 million. And that's the key to this 1 million experts. Now back to sparse MOE. Sparse MOE has become a very popular architecture these days, mostly because you can scale up your model without increasing the compute. But there's one question. So if you look at the scaling law, right? What the scaling law tells you is that if you increase the number of parameters, you're decreasing the loss and therefore increasing the performance of your model. But when you have a sparse MOE, we kind of have 2 type of number of parameter n here. There's one that's the active n, which is the number of neurons you actually use, the number of neurons in the expert you select. And then there's the total number of parameters, which is the all the set of experts you have in your model. Most of them you're not using. So the question is, if you're looking at the scaling law, which one is an effective n here in the scaling law? It could be that, because you're only paying for a small number of neurons, even though you're making the whole mix of experts very big, you're not gaining anything. So this question was studied in this paper, Unified Scaling Laws for Related Language Models by colleagues at DeepMind. What they found out was that if you use this rotate structure where you have different feedforward networks and you're picking one of them, and so what they show here is that if you fix the size of the base model, which is the size of one expert, and by simply increasing the number of experts, and every time you only use one expert, so the active number parameter and the computational cost stays constant, but just by increasing the number of experts, you can increase the model performance. So that's a good news. That means that there is a way to get your model better and make it larger, but not paying the compute cost.
Do you know how that scales as opposed to just increasing, say, numbers increase?
That's a good question. So that's on that. Next slide.
Then your training cost goes up.
Your training cost goes down if you make the total number. Yeah. So what they were doing was that they try to, so you have the mixture of experts, that's the loss you get. So you have the base size is n, you have E of the experts, right? So they were trying to solve the equivalent dense model size, where you just have one of this expert and then they should have the same. Then you get this plot. So given the base model size, and you have let's say a fixed E expansion rate, as you're increasing your model, your effective model size, of course, also grow. But the bad news they had was that this gain you get by using MOE is shrinking as you're scaling up. So at some point,
there's no advantage of using MOE anymore. That's what it got by extrapolating their scan model. So I think that you could kind of make counter claim, and that is once you have saturated your resources such that you need MLD so that you don't need to train all of your parameters, that's where you could perhaps bypass that. Your dark line is going to eventually just click because you're out of memory. Right. So
You're saying it's finite data.
finite DRAM. Yeah. So you could come up with many others, but the thing is, this turned out to be false.
Because otherwise we wouldn't have this talk.
Yeah, exactly. So this is a classical case of doing your research without understanding the scaling law and the optimal training. So what happened is that there's a small detail in their training details that most people just overlook, which says that models were trained with the sequence length of this and the batch size of that, regardless of the size of the model. And that's a big problem. You cannot regardless of everything. To understand why you cannot, you have to understand scaling laws and compute optimal training. So one way you can profile your model these days is to do an isoflop curve. What this means is that you choose a flop budget and you fix it, and you vary the size of your model, and at the same time vary the number of tokens you train on, so that you have a constant compute cost. But because you're varying both the token number and the model size, the performance won't be exactly the same. So what you get will be this kind of curve, like almost like a quadratic curve, where you have a point that has the lowest loss, which you call compute optimal point. And then around the compute optimal point, you have an undertraining regime and an overtraining regime. So what overtraining means is that you're training a model with the same budget on more data for a smaller model, right? So you're training on the more data than the compute optimal. And the other training one is when you're training on less data than the compute optimal. And so I'm taking an example from this paper, Mixture of Depths, where they were proposing this new fancy idea called mixture of depths, where you can dynamically allocate the compute for each layer. But it's not important what exactly this method does. The point is that they were trying to show with this graph that this method is better than dense baseline. But if you're not doing a isoflop profiling, if you just look at these 2 points, right? These 2 points here, and you could argue that, oh, I'm using the same compute for my baseline. I'm using the same compute for my method, and the baseline has lower loss. So the baseline is actually better. So not comparing the compute optimal performance will give you you can draw any kind of conclusion from your model comparison evaluation, right? And that's exactly what's happened with this MOE paper. When they're fixing the number of tokens and they're scaling up the model, both MOE and dense model enter the undertraining regime. And with severely undertrained, dense model actually outperform MOE. And this problem was discovered by a new paper, scaling law for fine-grained MOE. Was there a question?
No, I mean, that's counterintuitive because you would think that MOEs require less parameters. But
so when you're really large, on average, each parameter in the MOE is getting very little data to return back. So they're underdoing starting up here. Yeah. So this paper said, okay, if you also adjust the number of tokens to be compute optimal, like to co-scale the D and N at the same time, MOE is actually always more efficient. So they have this flops, scaling law over flops, where you increase flops, you always have this gap by using MOE. And they also introduced another axis of scaling, which is granularity. So they show that as you're increasing a model, the compute optimal granularity should also increase. So what is granularity? Granularity is basically the number of active experts in the active parameters you use for each token. So I'm showing two examples here. On the top, so both of them have the same number of total neurons and the same number of active neurons. But the one on the top has granularity 1 because there's only one expert in your active neurons. And the bottom has granularity 2 because now you're choosing two smaller experts. Even though they in total have still just 4 active neurons, there are 2 experts here. Think questions?
Sorry, I was just wondering, should you like is number of active experts over the total amount of active experts, or do you?
So N active is the number of parameters, number of active parameters.
Right, so that would be
And
there, right?
sorry.
Upper example plus 1.
So this will be 4 times the size of each expert. So number of parameters is you have 4 active neurons.
Yes.
Each neuron has parameters associated with it.
Right.
Right. So let's say your weight dimension is 1024. It would be 4 times 1024 times 2 because incoming and outgoing.
Yeah.
And N expert is the size of one expert.
Neurons full.
Or you can, well, actually, there's a constant. You can just cancel out the parameters associated with one neuron. So this is basically 4 neurons divided by the number of neurons in one expert.
Right.
Yeah. So this 4 by 4 is 1. 4 by 2 divided by 2 is 2. Okay. And they found out that you can get this new scaling law taking granularity into account. And as you're increasing granularity, you also get better performance, which also has this power law relationship.
Interesting about means you have more links in your graph. Essentially,
You have more logics in your feature.
Yeah. Still not quite getting it because the next start.
Yeah.
But
This one?
just said, yeah, this one here. So when you see model size here in this graph, so it's 64 times 3 million, 64 times 7 million. The 64 is still the number of experts, right?
This expansion rate. So it's a bit confusing their terminology. So they're saying that in normal baseline model, you have this MLP layer, which has some size. And in your mixer of expert, you're expanding that by multiplying 64 to get the total size of the mixer of expert. So 64 is, so 3 million here is the active number of parameter. And 64 is the expansion rate you get to get the mixer of expert.
Again, exactly. Granularity, your x-axis, that is related to the number of experts you've got, right?
Right. So if you use 64 multiplied with granularity, you get the number of total experts.
Yeah. Okay. Then understood.
Yeah. Okay, and they show that it's extrapolate to a larger size or loss. And okay, so what's the implication of this new scalar here? If you look at this formula, right, like with normal scaling law, we know that if you have more compute, what you should do is that you want to wrap up your D and your N total. So that's how you get better performance. So then when you have more compute, what you do is that you want to increase granularity, total number of parameter, and train on more data. That's how you get better performance. But at the same time, we don't really want to have a higher number of active parameters because that's the number you pay for, right? You increase the activation memory, it gives you more flops. So then what you can conclude is that the number of experts, which is E equals the N total times G divided by N active. So these two are going up. This stays constant or bounded. What this tells you is that number of experts should go up. And similarly for the size of the expert, this one is constant or bounded, and this one should increase. So the size of the expert should decrease. And if you take this to the extreme, what you want is a mixture of a million tiny experts.
Personally, does that factor in the cost of selecting which of the experts to use? Because it's
Yes.
like there's
Exactly. So if you look at this graph, here to compute which expert you need 8 logics, whereas here you only have 4, right?
So when you're increasing, let's say you make 1 neuron expert, then the cost to compute the router is the same as computing the activation. It doesn't make sense at all. That's exactly the problem I'm addressing.
Interesting.
So I'm proposing this parameter efficient expert retrieval where I have 1 million experts, very tiny. Each of them has just 1 neuron, the finest granularity you can get. And then you have to address this problem of retrieving that. And I don't want to compute a largest of dimension 1 million. That's too expensive. So what I do is I look into literature. I find a good learned index structure that you can integrate as a router. And this is called the product key retrieval. And how does this work? So suppose you're not retrieving 1 million objects, you're only retrieving 9 objects. What you do is that you take the 9 keys associated with your objects, your actors, you divide each key into 2 halves. And each of the subkey comes from a smaller set of subkeys. So you only need 3 subkeys in each set to get 9 full product keys. And why is it good? It's good because now when you want to retrieve, let's say, the top 2 out of this 9, you don't need to do a top key over 9 logits. What you can do is that you take your query, you also split the query vector into 2 parts. And you use the first part of the query vector to do an inner product with everything in the subkey in the first set, and the same for the second, and you do a top 2 out of each of the set. So this brings down the cost of top k to square root of 9, square root of 8. And of course, this will give you k squared candidate keys because you're taking 2 out of 3 in each, and then when you combine them, you get 4 subkeys. But the good news is that mathematically, you can easily show that the top 2 out of the 9 will be in this candidate key. So you can simply do another top k, which is much cheaper because you have a smaller candidate pool. And in total, and you can even reuse the inner product you already computed because the inner product of the full vector and query is simply the sum of the subquery and subkeys. So this brings the cost of 1 million logits to 1,000 logits because 1 million is 1,000 squared.
Sounds like a way better way to do thresholding inside. Like, in all seriousness.
Any questions here?
We go to the queue.
Can you do what?
Go to the queue roots.
Yes, you can just add another one. So this is extend to square root of sense order. Sorry, root of sense order. So then what I do now is that I'm replacing a feed-forward layer in a backbone, transformer backbone. And every time when I get an input, I map it to a query, I do the product key trick, I cheaply compute the top k indices, and I retrieve my experts, which then insert back to compute the output and then sum up the output of each expert.
So that's really a good part. So basically, you're replacing the linear algebra by search.
Yes, exactly. So you don't have to do
Everything to linear algebra to begin with. Look.
So here, the lookup is the search. But if you don't do the lookup, you have to compute all the logits of 1 million. So this is essentially an efficient way to implement the PWA.
Like you're doing a fairly linear in there, which can be sort of like look.
Right.
Because sparse activity means there's a couple of vectors in that's
Exactly. So that's how I implement.
so he's implementing directly index.
Yeah. So this is the kind of the pseudocode of the implementation. So you do the product key trick, you get the top k indices and the scores. Then you're putting all your experts. You know, each expert has this down projection weight, which is the blue ones, and then the up projection weights, which are the orange ones. And you can store them into 2 large embedding layers. And then when you want to do the computation, you simply do a ISUM over, so basically compute the inner products between the input and the down projection of logits, do the nonlinear activation, sum them up with softmax,
and then get back to your application.
So you're training the key.
I'm learning both the keys currently and the experts. You can propagate the gradient through the top key lookup. So the top key keys selected, they get gradients. The ones that are not selected, they don't have any.
And what guarantees you that you're not, since you're doing an optimization always to them instead of continuous, what makes it guarantee that it's not going to get stuck in somewhere?
Yeah, so that's actually an additional bonus you get from this. So because let's say you only choose top two, choose top one of this expert, you get gradient for this subkey, you get gradient for this subkey. You're updating also these guys and these guys. So there's a shared parameter. It's more parameter efficient. The price you pay is that the distribution of the keys have to have a structure that's this product structure. So if you look at if you put this into one, you project this high dimensional subvector into 1D, you're essentially getting the keys on a grades, 2D grades.
I see.
If that makes sense.
So it's really complexity of your data structure.
Yeah, but the good thing is that it's in the internal layer, so it doesn't have to be grounded to the data. The rest of the network can accommodate this structure.
I see.
But do you have to normalize to encourage equal distribution of starting?
Yes, there's a batch norm that helps. Where I will talk about the application of that. But even without that, it works pretty well. Surprisingly, I didn't think it would, but it did.
What's the results you're getting? You probably show us how many experts you actually need to one network or a big shot. I mean, the more you level them as far as in a sense, yeah.
So the more you have, the better the performance. That's the scaling law. So it's a matter of how many are you happy with. Like I use a million experts.
Yeah, a million experts. No, I'm saying how many of those million experts do you actually need to activate?
Oh, I also have a vision.
Okay.
Okay, so how well does this work? I've told you, you should not directly compare one trend model. You should actually do the isoflop because you might go run conclusions if you don't find the right. And I have 4 baselines. The first one is just a dense model by Nearline transformer without any sparsity. The second one is now popular MOE, but it's a coarse-grained MOE. So you have small number of very large experts. And I have 128 of them. Each of the expert has the same size as the MLP in the density.
Yeah, but your query search operations are not really flopped. So what does it mean?
Yeah, so they don't go into the flops.
They don't go into this isoflops.
They don't go into the isoflops. I just look up. It's data transfer. That you're paying for memory. But the thing is, for a dense model, you have to transfer all the weights into the wherever the tensor core or component you're doing the computation. Whereas for mine, you're only doing a subset of that.
That's what the isoflop.
Yeah. And I also compare it to the product key memory, which doesn't have expert, but it just combines the value vectors. And if you compare the compute optimal point, which this one, and you see that here has a lot lower perplexity. And these are 2 different flop budgets. This one is larger, that one is smaller. And the x-axis is log scale. That's why here it seems to be narrower. But if you plot in linear scale, it's actually much wider.
So what do you mean by perplexity? The log scorer or?
Yeah, it's the loss you use to train language models. It's basically exponential of the log lattice. And I also take the computer optimal model and then do some evaluation on different language model data sets. And I mean, there's nothing too interesting. It's just like it performed very well. And here's the ablation. So we have 2n, the number of parameters here. One is the n total, which corresponds to how many total experts you have in the layer. And you have the n negative, which is how many you actually choose to process your token. So on the left side, I'm doing an ablation with n total. So I take the compute optimal model in my peer layer, which has 1 million experts, and I'm reducing, so I'm dividing by 4. So every time I'm reducing the number of experts and still do the training with the same flop budget. And what you get is this, this curve. And the interesting thing is that this actually, if you try to extrapolate, this will cross the point of the corresponding base model that I'm using to get this. So I'm taking, so this model is actually this model where I take one FFN and replace by a peer model. So it seems that it's an interpolation between the backbone and this one with peer. And you're spending the same flop budgets for each of this point because it's isoflop. So what this tells you is that you can get better performance by simply adding more experts, which is sort of free because you only pay the memory to store the extra parameters. And those are a lot smaller than activation memory in your experts because you only have to store 1 copy for the total number of experts.
So the assumption is that the memory is free, right? And the memory is not really free, is it?
Memory is not free, and memory is, some might argue memory is even more expensive these days. Yeah. But I have a plan to resolve that, which is to offload all the experts onto RAM, and then you only have to load the expert you need into GPU to the company. So you're not occupying GPU memory. I have an intern working on that, but yeah, it's unfinished.
So that gets a lot difficult on fine grain. Your experts are right.
Yeah. Not really, because the parameter you're loading is still very small. It's very fine-grained, but you're using a small number.
So what is the footprint of your essential memory that you need?
It's the active number of parameters,
which is how many?
Yeah, which is, so I'm doing ablation. So the number, so I have multi-head retrieval, which is the edge here. That's the head number. And for each head, I'm retrieving top K experts.
Okay.
So the number of active neuron is actually H times K. And I'm increasing that. So from 32 to 64 to 128 and so on. And as you see that increasing this overall give you better performance.
Yes.
But it kind of plateaued because the more you have, the more flops you use for that layer. Right. And you have to reduce the data to get isoflop. Yeah. So it will saturate at some point.
Right.
So, and the funny thing is that it seems that as you're increasing this product, you should also increase edge to get the optimal performance. But so this is the number of the footprint of memory you actually pay per token. When you increase this, you increase the memory.
And that is what is the number? Can you give us just a number?
So I use 128 in my experiments.
It translates to how many gigabytes, megabytes?
I don't know, but it's small. It's really tiny.
And you're writing the cache. I guess that's what you say.
No, they have to be stored in HBM in
HBM.
Yeah. So you actually want to make this smaller so that this HBM is stars. That is a very rare resource.
Yes. So I see. Oh, so you really, that's your answer. Okay, really deal with it.
Yeah.
So normally in the normal kind of zone architecture, you concatenate all the ends together before it goes in the feed layer, which is like your next. So I need now see.
Yeah. So I don't concatenate them. I simply sum them up. So in this ISUM here, when I reduce, all the HK just got collapsed into the final result. So not concatenating, I just sum all the heads up. Yeah. So because for each head, I have this, each head has a bunch of this single neuron vector, right? So they each output a vector of the same size of the layer. I just simply sum them up. Okay, now another question one might raise is that I have 1 million experts. How many of them are actually used? It could be the router is only using like 100 of them, and most of the resource I'm paying in the memory actually gone waste. So I did an ablation here. I'm taking a data set, which is the validation set of the training data C4, and I do an accumulated statistic of the router score. So for every token,
for every expert, I can compute which for every token, I can compute which expert has been used. And then in that histogram, I add the routing score to the corresponding value, to the value correspond to that expert. And then I'll get a large unnormalized distribution vector. Then I normalize it to get the distribution of probability vector Z, which is basically the conditional probability of each expert being selected given the data sets you can move. And then you can compute two things. First is that you can look at how many percent of this probability vector is not zero. That means effectively how many are you actually using when you process the data. And the other one is how evenly they're distributed, which you can compute the KL divergence between this probability vector and uniform distribution. And as I'm increasing the number of experts, the usage is still around 100%. When it's a million, it's slightly lower than 100%, but that's good enough. Like that basically says, okay, you are using most of your experts in that million experts. And as you're increasing the number of experts, the KL increases. So it means that the distribution is getting uneven. So there are some experts that get picked a lot and the other not.
So is there something in your training that allows you to distribute them?
Yes, that's the query batch loss. So when I compute the query vector, which is this guy, I have a batch norm at the end. This will expand the space of my occupied by all my query vectors to make it evenly distributed in the space uniformly. Yeah. So then your key has to follow these queries to be used, and then this can be more evenly.
And that's how you are showing all your experts eventually kept busy all the time. Otherwise,
yes,
you'll be wasting experts.
Right. Then don't you incur a memory swapping out penalty? Like, because once you use the next mixture and then you have to put it back into another storage and bring another mixture back in.
So you can just discard it, right? Like, so there is some low-level optimization you can do to make this more efficient, which is that once you get all the indices in your batch, you sort them and you do a unique operation. So you pick the most often expert, you do all the computation, every token does the computation with it, you throw that away, and you load the next one, you fuse that operation together. Another thing that helps with even distribution is the product key structure. So if you don't have these shared parameters, let's say you pick the top 3 of them, they get gradient, they get trend, they're better, they get picked again. And then the rest of them just go starve with gradient. But because you have shared parameter, when these 3 get picked, all of them get gradients. They all get improved a little bit. So increase the chance of the other getting picked in the future. So here, you can see that if you use the batch norm, your KL is always lower. So that means the distribution is more even. But even when you don't use batch norm, you still get pretty good coverage of the experts.
That's just because your data, that depends on your data, right? Or what's the insight on that?
Yeah, it does. So if you have data that kind of just rely on, it's not diverse enough, you might get the collapse mode. But for the lecture model that I've tried out, just have so much data. Right? And another thing you can look at is the isoflow curve with and without the batch norm. So you do get better performance with the batch norm, but it's only more significant around the computer optimal region. When it's not, it's actually not clear that it's better. Yep. So
That's pretty cool. I think it would be a bit different type of network, right? I mean, it's not a normal network anymore because basically every one of your neurons is now I'm thinking of it as like a 2-compartment thing. And one thing that gets the other parts, like you do that left of individual neuron.
Yeah.
So what it is around.
Oh, sure.
I mean, you kept talking about the routing, without an output, but that's about all routing.
Yeah. So like you can think, this is also related to the RAG method, like retrieval augmenting model. But in RAG, you're augmenting with data, whereas here you're augmenting with model standards. So, and I have some future plans for this, which I've not presented here because they are confidential. Yeah, but you could imagine this is creating opportunities for CPU computation. That I'm also working with a team at the TPU team. They're using the sparse core, which is a specialized hardware in TPU that's embedded for embedding lookup. So they,
But it's yeah, but you're not really you're not doing it's not that's the market ladder.
There you go. Problems not really GPU optimized anymore. This is more like a trillion tiny CPUs you want to run that problem on, right?
Yeah. So, but then it's a lot cheaper to get a bulk CPUs because the computation is actually very low. What you want to do expensively is manual operation.
They don't need to be told.
Yeah.
So this is, I mean, obviously this takes ideas from like ensemble methods and like older stuff that people have found, like the expert models and stuff. And something I remember that it was always a discussion is like you have to choose like how many experts you pick versus how complex they are. And if you here kind of made a decision that you want the expert to be a single yarn, right? But in principle, you could also say, well, one of these experts could also be a tiny here. And you could get the small, like, you know, like instead of 1 yarn, it's like a tiny.
Yeah, but this the granularity is still a lot healthier. The smaller, the better.
But actually, so you know, with smaller, but also in depth smaller. Like you want to have you want to have within one layer. You want to have a lot of experts versus having experts where each expert is multi-layer. That's a different dimension, right?
But if you think about it, so here I'm using top K, right? I have this edge K, and I'm summing up the contribution of each expert, which is essentially dynamically assembling a MLP of hidden dimension HK. So it is using a higher dimensional MLP. It's just that it's dynamically created.
Right.
Yes. And you can like if you rewrite this equation of MLP, vanilla MLP of fixed dimension here. If you look at this is essentially also just a mixture of experts, with all the experts always contributing to the output. Yeah. So there's really no difference between taking one neuron and put them together or taking a group of neurons. It's just more rigid with a group of neurons because you're always using the neuron. Maybe they don't really contribute, but you're still taking them. So why is it better than this coarse version of mixture of expert? Because like, let's say you only want to know the knowledge of the capital of Ireland is Dublin. That's the example using this knowledge in your paper. In this expert, maybe this expert is specialized in capitals of different countries. So they're all stored in this expert. But only 1 or 2 neurons are responsible for the capital of Dublin. Now, if you do coarse routing, you're still picking all the other neurons for other countries. And you're paying cost for that, even though you're skipping all of them. When you have fine grain, you can precisely pick the one that tells you what's the capital of Dublin.
What I was thinking is that you have another layer of neurons, right? You have not one layer that you're getting with your getting store here, but you have like an MLP. But yeah. Your expert sound is an MLP, but I mean, I guess it's probably not worth it.
It's not doing
across multiple layers. Right? If you have this, yeah. So do you know in your models, do you have like one layer of this, like a million experts in parallel, and then the next layer is something else, or is the next layer again like?
No, so I only replaced one because if you look at the size of my experiment, well, this is a log scale, so you don't see, but here is already 7 billion just for one layer. So if I have, let's say, 12 or 24 of them, it's too large for my experiment. Yeah.
One layer, that's really good.
It's just one layer. Yeah. I could also distribute this Amelia expert into different layers, but I want to make a point that it's possible to do Amelia experts.
That's cool. Yes, coach.
Because they didn't quite get the hard number for the dynamic sparsity. So how many out of million experts on average are you activating at any given point in time?
what's going. So I impose it to be 128. Maybe it's using less than that, but I would
1 in 1,000, second year, 1 in 800. But you say you have a billion experts.
Yeah.
So I believe divided by million gives you 1 in 800 or so, 1 in 900. Great.
Yeah.
Yeah, well, 1,000 is quite a bit, but yeah. Yeah.
But probably you don't need all of that. Like, so in the future, you could also think of the dynamic. You can dynamically allocate how many experts you want to use and generalize different numbers. So depending on your budget for difference, you can change that.
So clinical resources to run models and experiment with this. What kind of compute resources it is?
So right now I'm training on TPUs because that's easily scalable if you work at Google. In the future, once the TPU team helped me implement on Sparse Core, I'm running some Sparse Core. But I also think it's a good thing to offload the expert onto CPU because the computation is so little. You can do this fast on CPU and then only send the result back to engineer to engineer that to the rest. And this could, so RAP is a lot cheaper than GPU. So if you're a poor PhD student who can only afford one GPU, what you can do is that you offload 9 billion, 70 billion parameters onto your RAM, and then only do the computation for the attention layer on GPU, and then you can effectively run a much larger number on a much larger expert model with just one GPU.
Yeah, so I think this was what you were alluding to earlier. So you always didn't want to do both.
Right.
And so now if you went to multiple teaching places, you were doing RAP, they were also indexing the same as data center.
Right.
So it seems like that's another approach you could go to extend sharing.
To share the...
Yeah, because you want to have lots of experts. You don't want to happen.
Yeah, it's interesting that you said
more around that.
Yeah, so there was actually a paper I only found out later that it's called one wide layer is all you need. I mean, in your transformer, you just need one very wide layer and you repeat it. And that's as good as many smaller layers.
Yeah, but I'm saying you don't repeat. You use a RAP, you do it so like all the functional people is indexing to at the end when you straight on.
But in a sense, you're sharing the database.
Exactly.
Yeah.
Give us some solid skills to other problems of this theory you've trained on, like, to help there. But how is that? Have you tried it for other things? Look for
did I? No, I'm sure. Yeah, but mechanically you can put this in any conversation. Yeah.
But with the scaling logic the same, like with again for if you change distribution of a macro language model.
Right. So the scaling law of other modality that's for example for visual is an interesting question. So people don't really see a very clean exponential decay. Maybe there are new paper I'm not aware of, but last time I spoke to a vision expert, they said it's not so easy to get that. So if you look at the multi-model like VLMs people have, the vision part is a lot smaller than language part. I think it's not because vision is a simpler problem than language. Maybe it is, but I think the problem is that using bigger model doesn't really give you advantage because they haven't found a way to really leverage a lot of vision data. So when you train vision model, you easily get overfitting when you use a very large model, but you don't get this with language. With language, it's still more data, just get better and better. It's quite helpful as a machine learner because you don't have to worry about overfitting.
Oh, I see.
Yep.
So this is ready for language.
This standard, but this architecture you can throw it in our vision.
Also, Victoria's fancies.
Yeah. So I have other colleagues who work on mix-up expert for vision models. They also, they don't have this big retrieval thing, but they have like soft MOE and stuff. So when they improve MOE layer, they also get a better performance in vision models. So I would imagine this can fast, but I have no idea. So.
No, but the key trick to make this work really is this product, the retrieval thing that's cheap to compute, which expert doesn't.
Right. Yes, without this, it would be very expensive. But you don't. So people have studied retrieval for a long time. There's only one technique to get this. There are also logarithmic stuff next to retrieval with binary tree and stuff. And
they can be learned as well. I just picked the easiest one to and kind of open up the space for people to explore. Maybe you can find better, more efficient ways of research. There's a couple of PH guys from the weapon last year. They did similar things. So you have these experts at the single level, and they had a low complexity search for the individual expert. I mentioned that in my review, so exactly that. There's only one drawback of their method, which is that when you train it, you have to propagate through all the nodes in their tree. So the complexity for training is not logarithmic, whereas this one is very deep for training. Yeah, I'm happy to take more questions offline, and the paper is on archive. With the same kind of reach on its side. Which one the paper you
found it, but it doesn't have time. That's the union mixture.
Yeah, it doesn't have any. It's this paper.
Yeah.